Hello everyone, and welcome to this video on section 3.1 called Integration by Parts. All right, so in this video, I'm going to be taking you through a sample version of a Newton-Alta assignment on section 3.1 called Integration by Parts. Please understand that, in this video, the questions that I'm seeing may not be the same as the questions that you see if you're working on a Newton-Alta assignment for this same subject. But the objectives should be similar, and I'm hoping they're similar enough so that when you watch this, it'll help you out, when you're doing the things by yourself. All right. So here's how they look, right? You got the title of the assignment in the upper left-hand corner, your mastery bar in the upper right-hand corner, right, telling you how far along you have gotten, your activity log, shows you how far through each objective you've completed. It has a progress circle for every objective. And it looks like this assignment has, I'm looking at, has 5 objectives broken up into 2 areas. So we're going to have a bunch of indefinite integrals. And then afterwards, at the end of the video, we'll have a bunch of definite integrals to evaluate. All right, then you have a question related to a current objective. And at the bottom of every question, you should have some sort of feedback button, right? So if you're seeing any issues with the question itself or the answers given, typographical errors, whatever, you can send feedback directly to Newton and maybe they'll help you out. Maybe they can fix things. You will not have this instructor cheat button, right? This is for instructors only. You will have a more instruction button. So if you're ever struggling with a particular objective, try clicking on this. It'll take you to a page with more instruction, either some reading or some videos to watch or both. And then you'll have questions brought to you with the instructions still up and visible. So maybe you can refer back to it and maybe that'll help you get through the assignment as well. All right. So we're doing integration by part. My first objective here is use integration by parts to find indefinite integrals. All right, so the first one I'm given here, well, before I get into this first example, let's talk about integration by parts. All right. Okay, so I'm in this chapter 3 of this particular, Newton Alta Calculus 2 course. And in chapter 3 is all about techniques and applications of integration. So integration techniques to start. And this is one of those, right? Integration by parts. So they kind of skip over U substitution. So I think they're assuming that you've learned U substitution from Calculus 1. All right. So recall something first from Calculus 1, though, all right, to develop this. So suppose we have functions, f of x and g of x. So we're given 2 functions of an independent variable called x. And remember, if I want to differentiate their product, so the derivative of, f times g, with respect to x, remember that this is you're going through the product rule here. So recall, I mean, I like doing it this way where it's, I leave the first function alone. So f multiplied by the derivative of the second function, right? The derivative of g with respect to x plus, right? Plus, and then you just switch them up. You leave the second function alone, right? G of x multiplied by the derivative of the first, right? The derivative of f with respect to x. Oops, don't want all that. Just the derivative part here. Sorry about the, make the bar a little shorter here. Just the derivative of the f, right? I guess you could extend it. It wouldn't make a huge problem. All right. And then if I were to, now again, you can only do this really with first order differentials. If I multiply through by dx, this is telling me the differential of a product of two functions, say f times g, is equal to, the first function multiplied by just the, basically all the dx's can go away here, right? If I were to multiply, again, multiply, quote unquote, here, through by dx. First function times the differential of the second, and then add to that, the second function times the differential of the first. And just to save on a little writing here, you're going to see very often they're going to call f of x u of x, but they'll just say it's u. All right, so u is some function f of x, and if we call and they'll call g of x v, right? You don't have to use the letters u and v. I'm just using the letters that you're going to typically see in some sort of calculus textbook. All right, so if I do that, right, then this rule here becomes the following. The differential of u times v is equal to u times the differential of v plus v times the differential of u, right? Just to save on some writing here. And then we'll integrate both sides. Right? Do the indefinite integral of both sides, right? So now I'm doing this, right? We got indefinite integral of this, and then same thing over here. We'll integrate both sides. Now, remember integration and the differential symbols, the integral and differential like undo one another, like inverses, kind of. So this left side is just going to be u times v, and the right side, right, the integral of a sum is the sum of the integrals, right? So I can express this as the integral of u times the differential of v plus the integral of v times the differential of u. And then we solve or solve for this part that I just boxed here. And we'll get what's called the integration by parts formula. So so here's our parts formula. I'll call it the parts formula. So we're taking the integral, if we get this alone, we have the integral of u times the differential of v is equivalent to u times v, so just uv. And then to get this alone, right, I would subtract this integral of v times the differential of u. So minus the integral of v times the differential of u. All right, this is huge. All right, this is what I'm going to be using for the rest of this video, right, for all the examples in the video. So what we're doing, okay, when we're asked to integrate something by parts, right, we'll be asked to integrate some expression, right, will be on the left side here. What we have to do is choose a u, something to represent u from the integrand, and then also something to represent the differential of v. Right? And because remember, a differential of something is going to involve another differential. The differential of f would be, f prime times dx, or so is f of x. So we choose something in the integrand to represent u. We choose the rest of it, right? The rest of the product with the differential involved, dx, dt, dz, whatever it is, to represent dv. And we need to fill in the rest of the stuff. All right, so we'll know u. We'll have dv, so I need to find v by integrating. All right, well, I'll go through all this many times in this video. Hopefully it'll make sense after several examples. So yeah, we just gotta fill in this stuff over here. And we'll have u, we differentiate. So I'll write this up. All right, so we're gonna choose from over here, we're gonna choose a u, and the rest of the product, the rest of the integrand to be dv. You're then going to differentiate, I'll put diff. You're going to differentiate the u to get du. All right, and then the dv, you're going to integrate. I'll put int for integrate. You're going to integrate the dv to get v. All right, and once you've found du and v, you're going to put all that stuff over here. All right, you're going to take the product of u and v and then subtract the integral of v du. And I'll do this in a little chart form later, but we'll start off doing it the long way right now. But this is it, okay? This is the whole procedure for integration by parts. So now let's finally look at our first example. First question here, we have the integral of negative 2x times the cosine of 4x times dx. And typically, not always, but it's a good idea to use integration by parts when the integrand is a product of two different kinds of functions. So you see I have negative 2x, that's a polynomial function, and then times the cosine of 4x, that's a trigonometric function. So if I see a product of, a polynomial and a trig function, or maybe an exponential and a trig, or a log and a trig, or a log and a polynomial, whatever, it might be a good idea, right? It doesn't always work. You got to be careful with integration because there are some integrals out there that you cannot express in terms of the elementary functions, right? The elementary functions are all the ones you learned in pre-calc, you got your polynomials, your rational functions, your radicals, your exponentials, your logarithms, your trig, your inverse trig, your hyperbolic functions, right? Those are the elementary functions. There are some integrals out there that cannot be expressed in terms of elementary functions, right? You got to use power series or some specially defined functions to be able to evaluate them. But I'm hoping that, because this is an introductory section here, we're going to see nothing but integrals that we can express in terms of elementary functions, right? That we can use integration by parts for. Anyway, that's neither here nor there. Sorry about that tangent. So yeah, I got a product of two different looking functions here, so that indicates to me it might be a good idea to try parts. So let me write this out. So we have the integral, right, of negative 2x multiplied by the cosine of 4x, times the differential of x. Now you can play around with this, all right? Your choices for u and dv, you can do really whatever you want. It's just some choices are better than others. So let me go over here and show you a bad choice, right? I'll call this a bad choice. And no choice is really bad. It's just some choices will be worse than others. Okay. Uh, Let me show you. So if I go in here, I want to think of this, right? This is the left side. This is the integral of, something I'm going to call u times something I'm going to call dv. So let's say I were to call, then you just pick a factor here, right? Pick a factor from this product. Again, without the differential, right? U won't have the differential. dv, okay, dv must contain the differential. Point that out. Well, let's say I called the cosine of 4x. I said that was u. Now, let's make that my u. U equals cosine of 4x. And then the rest of it, okay, if that's u, the rest of it, including the differential, has to be the dv. Okay, so this and this are making the dv, right, the differential of v. It's over here. dv would be negative 2x. Right. So like I was saying, you make these choices first. Break up your integrand into a u and a dv, where the dv has the differential. And now, fill in the other side. uv minus, and then the integral v du. Well, I've got u. In order to get v, right, I need to integrate, put int, or maybe put the integral symbol there. I need to integrate both sides of this. Now the integral of dv would just be v, and the integral of negative 2x dx, right, that'd be negative x squared. And you don't have to, you can put plus a constant if you want, but that's going to throw things into some craziness. So just have the constant be 0. All right, make it simple for yourself. So no, don't worry about the constant of integration. So we're just doing the most basic, the primitive, or the most basic antiderivative of negative 2x. All right, so now I have u, I have v, and I can fill these in, and I can fill that v in there. Now I want du. I have the differential of v. I don't have this differential of u, so that's where I'm going to take my choice for u earlier, and we're going to differentiate. All right, so I'll put the d dx here, whatever the derivative symbol. And when I do that, right, we'll have the differential of u equals, and then remember, differential is something, it's just the derivative times the differential of the variable that the expression depends upon. So remember, the derivative of cosine of 4x, that would be negative 4 times the sine of 4x, right? I used the chain rule there, right? It would be negative sine of 4x, but then times 4. And then times your differential of x, right? And there's your du. All right, then if I go through and fill in the parts formula, all right, so now I'm going to take this integral we started with here and fill in the parts formula. All right, here's how this goes. In my little u dv, v du stuff over here, you're taking u times v, right? You multiply these, all right? So it's u times v. So cosine 4x, that's the u, times v we saw as this negative x squared. Okay, so there's uv, then minus the integral of, and then v du, and here's where that's coming in here. There's a little overlap here. All right, we're gonna minus the integral, right, of this product. So you'll see sometimes people will write that, and I'm going to do something with a chart later, a little table method that'll make things, so that you can just do it. It's a little bit of a shortcut, so you can do less writing. It's not really a shortcut, but just less writing. So very often people put plus here, minus here, and just go, you're doing positive UV, do this diagonal thing, and then go horizontal, go minus the integral of this product. All right. And then you kind of keep going down the table. Anyway, but we're doing minus the integral of v, right? V was this negative x squared, again, right? There's v, and then du was this, right? Times negative 4 sine of x. Oops, sorry, sine of 4x. That's a 4x, sorry, that's a 4x. Negative 4 sine of 4x, and then, times your dx, of course. Now, if I were to simplify things a little bit, we're getting here, negative x squared times the cosine of 4x. And then here, this is a minus, and negative times negative is plus. This is still minus, and then the integral of 4x squared, right? This is a positive 4x squared times the sine of 4x. And then with respect to x, right, times dx. All right, so look what happens here. Look, now I start with one integral. I got something out of it, cool, right? Negative x squared cosine 4x. But now I have another integral to evaluate. And this is actually this is even worse than the first one I did. The first one was a linear polynomial times a trig, and we just made it more complicated, right? Uh, this is worse than what I started with. Right? Again, because the power on that polynomial went up. It's a more complicated integral. So if you get stuck like this, or you realize, hey, when I do parts if I make this choice of u and this choice of dv, and I start doing stuff, filling that formula in, right, the parts formula, and I go through it and I realize, oh, this is going to get worse and worse for me, then you have to make another choice. You have to go back. If it's worse than the beginning, or you don't see how to continue from there, go back and start over. Okay, you might have to play around with some of these. Right, make new choices. All right, well there, I chose u to be the trig function and dv to be the polynomial. Let's do it the other way around instead, see what happens, right? You have to play around with these things. And so again, there's the parts formula. Let's do another, this over, blank. So there's the parts formula again. So let's do that again. Got the integral of negative 2x times the cosine of 4x, times dx, of course. But this time, I'm going to have u be the negative 2x, all right? So again, just think of this as a product, and we're going to break it up into two factors, one called u and the other called dv. And again, dv has to contain the differential. So u is 2x, and then my choice for dv is got to be the rest of it. So u times, so the rest of this is dv, right? So I can break it up into u times dv somehow. So dv is cosine of 4x dx. Right. Now I'm trying to fill in the other side. Right. It should be equal to u times v minus the integral of v du, v times du. So I need du, right? So again, we differentiate. I'm just going to put diff now. Find the differential of u, find that du. So du, right, would be the derivative of negative 2x with respect to x. That's negative 2, right? And then times the differential of x, right? Times the differential of the variable that that expression depended on. And then for v, right, we have dv. If I want v, right, I'm going to integrate. And that'll give me v over here. And then the antiderivative of cosine of 4x, right, would be sine of 4x, but then times a quarter. Don't forget, right, because you're going to be, if you were to differentiate, you'd have to multiply by 4 with the chain rule. And when you do this integration, once again, don't worry about the plus constant, right? Just call it 0. Great, so now I have my du, I have my v. Let's go into the other side of the formula here. So this was the integral of u dv to start. And that says equal to u times v. Right? So u is negative 2x times v. Right? So times here. Right? So times, 1/4 times the sine of 4x. Then minus. Okay, so that was uv minus the integral of v. So now we're doing minus integral, right, of these two, the product of these two. So you're doing like this zigzag motion, because we're going to have more later. We're going to have some examples later, I'm sure, where there's more lines to this, and you're just going to kind of do a zigzag thing. Yeah, so anyway, minus the integral of v du. So v is a quarter sine of 4x. And then du is, negative 2 dx, right? And I'll simplify some things. So this is negative 2x times a quarter. Negative 2 times a quarter is negative half. And then you have x times the sine of 4x, right? Negative half x times the sine of 4x. Okay. Then minus, now look here. If you multiply these constant factors, negative 2 times a quarter is negative half. And I'm going to pull that negative half out, so this becomes plus half. Hopefully you understand that, right? Pull the minus out, makes it a plus. And then, 2 forces a half, pull that out. Still have an integral. And what's left over in here after pulling the constants multiples out, you got the sine of 4x. Ah, this is much better. All right, do you see now, right? I started with a linear polynomial times a trig. This integral I have to do here is just a straight up trig integral. Not a problem, right? There's no polynomial being multiplied by other than 1. I guess you could call 1 a polynomial, but yeah, this is a lot easier, right? So this looks like it's going to work out. Now I can evaluate this. All right, so we have negative 1/2 x sine of 4x, and then plus, 1/2 times, right? Now I'm doing the integral. I'm actually integrating this, finding the antiderivative of the sine of 4x. Well, that would be negative, cosine 4x. Then again, don't forget times the quarter, right, to counteract the chain rule. That's the antiderivative of that. And then after simplifying, negative half x times the sine of 4x. And then half times negative a quarter would be minus 1/8 times the cosine of 4x. Right, and I'm done. And then don't forget, right, when we're doing indefinite integrals, right, there are no limits of integration here. This is what would be called the primitive antiderivative, right, or the basic antiderivative. But don't forget, you can always add any constant to this, and it would still be true. Right. So don't forget your constant of integration, please, right? For indefinite integrals, right? For definite integrals, you're just going to get some number at the end, some value. There we have it, all right? Now, if you want to check this by hand, right? I'm only going to do this for this first example. Remember how to check integration, right? If I want to check if my answer is correct, remember this is the antiderivative, of negative 2x times the cosine of 4x, antiderivative. So if I want to check that this is correct, I take the derivative and see if I get the integrand, the original integrand back, right, after simplifying negative 2x times the cosine of 4x. So we're going to take this antiderivative we found, and I'm going to differentiate, right, with respect to this variable. And see, hopefully when we're done, we get negative 2x times the cosine of 4x back. Okay. So the first term I'm going to have to use the product rule for. So if I call this y, we're going to say y prime then, or dy dx. That's a product rule, negative 1/2 x times, and then the derivative of the sine of 4x would be 4 times the cosine of 4x plus, and then this leave the sine of 4x alone times the derivative of negative 1/2 x, so just negative 1/2. Okay, so there's the derivative of the first term, product rule. Then we have minus 1/8 times, and the derivative of cosine of 4x would be negative 4 sine of 4x. And then, of course, the last term is just a constant, so plus 0, but there's no real need to write plus 0 there. All right, now after simplifying some stuff, right, this first term here would be negative 2x cosine 4x. Next term would be minus 1/2 the sine of 4x. And then the last term here would be plus 1/2, right? 4/8, negative times negative, plus 1/2 sine of 4x. And oh, beautiful, right? These go away, right? Those add up to nothing. And this is the integrand I started with, negative 2x cosine 4x, right? This is what I started with, right? Negative 2x cosine 4x. Beautiful. All right, so check our antiderivative here is correct, right? This indefinite integral was correct. Wonderful. I guess another way you could check it, another way you could test this is go to Desmos. And if you recall how to define, well, let me just do this here, right? Recall how to define an integral as kind of an area accumulation thing. I could define this as the integral from, some constant, say a is a constant, to x of, and then just use t, use a dummy variable t here. This would be negative 2t times the cosine of 4t dt. And I can use any constant I wish here, right? Because remember this would be, let's say I call the antiderivative of this capital F, right? Say this is capital F of x, and this would be, capital F at x minus capital F at a, and the derivative of this would be just little f, right? If this was little f, I don't know. You remember the fundamental theorem of calculus, I hope, right? The derivative of capital F should be little f, right? The derivative of this would be little f again, right? Because this last part here is a constant. So we could define things as a kind of a definite integral, but with variable limits. So if you want to check on Desmos, let's go integral, right? Because it puts up definite integrals. I'll just go from 0 to x of negative 2t, and I'll call this y equals, right? So, well, actually, it'll graph it anyway. It'll be some function of x, right? Y equals negative 2t times the cosine of 4t dt, right? You see that there's your graph. That is our integral, right? And let's see, let's put in y equals what we got as our answer. So this integral up here represents the original integral, and we can put in what our answer was, right, without the plus c for now. I guess you could put plus c and then just change it until the graphs match. All right, so maybe I'll do that. But so yeah, y equals our answer ended up being negative 1/2 times the x times the sine of 4x, and I'm in radian mode, by the way. Uh, then after that, I had minus 1/8 times the cosine of 4x, right? And then plus some constants, right? And I'll add a slider for this so we can move our. You see how the graph of our blue curve there has exactly the same shape as the red curve, and if I just move it, slide it down a bit here, where C is like, it looks like it's a little off here. So maybe I should have picked a if I wanted them to match perfectly, you know, I can move it around until they match perfectly, right? It doesn't really matter though, but the shapes of the graphs are exactly the same. So the correct my answer is if the shape of your graph when you enter the antiderivative is the shape of the initial integral, define it as an integral function, you got the correct answer. All right, so that's just another way to check without checking by hand. All right, so after all that, right? Sorry, this is just the first problem, but I wanted to explain a lot of things, right? The other ones should be a little faster because I'm not going to do all the checking all the time. I'll do it for the first couple, but all right. So we ended up with right negative 1/2 times x times the sine of 4x, and put that in parentheses. Remember, it says here in the instructions, be sure to place the argument, right, which is another word for like the input of the function. Be sure to place the argument of any trig functions or logarithmic functions in parentheses in your answer. So that's why I need 4x in parentheses, and it's inside a trig function here, okay? So negative 1/2 x sine of 4x, and then we had minus 1/8 times the cosine of 4x. And then don't forget, plus c, right? You got to add some sort of constant here. All right, notice it's an indefinite integral, so typically you'll throw on plus c. Now, I don't know if they want a capital C or a lowercase c, but I'm hoping this c will be enough. And wonderful, yeah, so they have a capital C in the answer. If you put a lowercase c, notice it still takes it, all right? But you got to have that plus c, okay? If that plus c is not there, it's not correct. You're not giving the general antiderivative, you're just giving the primitive one. And they want you to describe all of them, of course. All right, now after every question, you'll be given some sort of answer explanation, whether you get it right or wrong. I would suggest reading over these, especially if you get it wrong. If you get it right, maybe reading through it will help you. Like, maybe they do it in some other way that you thought, oh, wow, that's easier. I'll do it that way next time. And of course, if you get it wrong, uh, read through and see if you can figure out where you went wrong. Right. And notice in the answer explanations, I'll get to this in a second. They mention this LIATE mnemonic device, a little acronym here, LIATE. I'll point it out. I'll tell you what that means in a second, but it doesn't always work. It does a lot of the time, sure. And for a lot of these examples, in this introductory section, I'm sure the acronym or this mnemonic will help you, but it doesn't always work. All right. So I personally like just kind of playing around. If I'm trying integration by parts, pick a U, pick a DV, go through it, see what happens, and if it ends up being ugly or something that looks worse or harder to handle than the original integral, I'll start over. All right. Sometimes it takes trial and error with these things. Yeah. I had a calculus instructor a long time ago say to our class, differentiation, right? Taking derivatives, science. There's definite ways to do it. You did it every time, and the derivative of some function, some elementary function. But integration is an art, right? Integration. Remember, I said earlier, there are some integrals you might come across that cannot be expressed as elementary functions in terms of elementary functions. And the methods and techniques to integrate vary widely. And sometimes you have to get creative, like an artist. So differentiation is a science, integration is an art. I'll keep passing that along like my high school teacher did. Okay, so again, another tangent, I apologize. Okay, so let's continue on. All right, so another one where we're asked to use integration by parts to find, some indefinite integral. Right, so here I have, integral blah, right? Natural log of 2x to the fourth divided by the square root of x. Uh, yeah. All right, so let's go to our paper. And I'll explain that mnemonic device now real quickly. First, I'll write this, right? So we're doing the integral of the natural log of 2x to the fourth, right, divided by the square root of x times, dx times, I'll always have that differential there at the end. Right, so here's a mnemonic device that was mentioned in the answer explanations after that first example. Right, a mnemonic device is just, Mnemosyne was like a Greek goddess, a muse about memory, right? She was all about memory. So mnemonic devices are just simply, little tricks, little things to help you remember something. This is a mnemonic device for I'll put best in quotes here because, like I said earlier, this this device, this little acronym I'm going to throw up at you, doesn't always work. Right? It doesn't always work. I prefer just kind of playing around, pick a U, pick a DV, find Oh, and I forgot to show you the chart method. Well, I'll show you the chart method here for this one. After this, don't let me forget. I'm sure you'll remind me. So for a best choice of U, right, a best choice of U in order of importance, right? In order of importance, we have Liate. I've also seen this written as Lipty. It's like Lipton iced tea. So first, are there any logarithms? All right, because the integral of just a plain old logarithmic function, right? You'd have to do parts with that. You don't know that from Calc 1. The integral of just the natural log of x by itself. So I'd rather not, you know, integrate that. I'd rather differentiate that, right? So I'll choose that for you if I see a logarithm as part of my integrand. So that, again, that might be a good choice for you. It might not be the best one, but it could be a good choice. Now, if there are no logs, are there any inverses? So like inverse trig functions. I'll say inverse trig. Are there any inverse trigs? Inverse sine, inverse cosine, inverse tangent, stuff like that. Or arc sine, arc cosine, arc tangent. Because again, back that you saw in, again, if you're thinking Calc 1, the inverse sine function, inverse cosine, you didn't see how to integrate those, right? Those weren't given in Calc 1. So I'd rather differentiate those, right? So I'll make a choice. I'll choose those for u, and we gotta find the du by differentiating. All right. Then after that, your arithmetic. These are your polynomials and radicals. Oops, polynomials. polynomials, possibly radicals, things with fraction powers, right? But think, uh, you know, expressions that can be written as sums, differences, products, quotients, and raised to rational powers of x. Now these you could integrate in Calc 1, right? Polynomials, radical functions, but again, we're saying maybe it would be easy to differentiate them as well. Of course, you're only picking this for you if these aren't present. And again, it might be better to choose. Like, I'm sorry to say this, but like, this is fine sometimes. But they do, I know a lot of books tend to bring this up, this Liate thing. Then after that, you have trigonometric functions. I'll just put trig, so set your sines, cosines, tangents, and whatnot. And then after that, exponentials. Exponential. Now, I'll say that these last two, in most cases, are pretty much interchangeable. If you had an exponential and a trig function in your integrand and you chose u to be the exponential uh, versus u to be the trig function, you're probably not going to go wrong. Alright. But yeah, so this is a little device here to help you in some cases, right? This doesn't always work. I know I've been saying that a lot. I'm gonna actually make that note. Uh, this does not always. Most often in the beginning section, right, an introductory section like we have here, it will. But in the future, this does not always give us the best choice of u. Please, please, please be aware. All right, well, still, for this example, I'll try using it. Okay, it can't hurt to try it, right? It's obviously brought up in a lot of textbooks for a reason. Works, works a lot of the time in introductory courses. So I'm noticing here, I've got a logarithm, right, in the numerator. So that's like, hey, if you see a logarithm, maybe have that be your choice of u. Right, so if I'm doing parts, remember I'll write the formula up again. You got the integral of u times dv. Right, we make a choice of u. The rest of it with the differential is dv. It's going to be u times v minus the integral of v times du. Right. So if I'm following this, if I want to try this out, right, this Liate thing, I see a logarithm up here. So I'm gonna have that. I'm gonna choose that to be u. This logarithm, natural log of 2x to the fourth. Right, that's going to be my u. And then the rest of it, right, will be the dv. Right, so again, and I said in the first example where the dv always includes the differential, right? So there's the differential of v. Now, this is dx, over the square root of x. I'm going to think of this as x to the negative 1/2 power times dx. Okay, make it easier to integrate. So we have u and we have dv. All right, now that's this side. If I want to fill in the other side here, I need u, I got v, I need v, and I need du. So to get du, right, we differentiate the u, the choice of u. So du is just, the derivative of this expression times the differential of the variable the expression depends upon. So the derivative of the natural log of something, right, was 1 over that thing. All right, so 1 over 2x to the fourth times, and then chain rule, derivative of the thing inside would be 8x cubed. And of course, we'll simplify this, and then, times the differential of x, right, times dx. So after simplifying, the du, it can be 4 over x dx. 4 over x, right? 8 divided by 2, and then x cubed over x to the fourth, right? Okay. And then to find v, right, you take the choice for dv here, and we're going to integrate with respect to x, right, as dx. All right, so v, doing some simple power rule thing here, is going to be raise the power by 1, so x to the power of positive 1/2, and then times the reciprocal of that new power, so 2x to the half. Don't worry about the plus constant here, just make it 0. Okay, so I have du, I have v. Now I can go into that other side of the formula, the parts formula. So our integral that we started with, right, the integral of natural log of 2x to the fourth over the square root of x dx can be equal to u times v. So the choice for u is the natural log 2x to the fourth, right, times my choice for v, not my choice for v, after I took dv and integrated, v is this 2x to the half. Right, times 2x to the half, or 2 times the square root of x, if you want. So there's u times v minus, and then the integral of v times du. So v, once again, is this 2x to the half times, and then du, right, we saw du after differentiating u is 4 over x, and then you have the dx afterwards. So 4 over x, or 4 times x to the negative 1, and then your differential of x, right? And after some simplifying here, this is 2 times x to the half, or 2 square root of x, times, and then your natural log, I'll put this in front, natural log of 2x to the fourth. Minus, and then here I have 2 times 4, so I'm going to pull that out. That's 8. Constant multiples couldn't come out of integrals. This is x to the half, times, this is 1 over x. This is x to the negative 1. X to the half times x to the negative 1 would be x to the negative half again. And look at what happens, right? I started off with some integral I definitely didn't know off the top of my head. And then through this integration by parts, I end up over here, and I got something here, great. Then I end up over here with an integral that I can very easily take, right? This is just an integral of some power function. So I can reverse the power rule for. So this is 2 times, the square root of x times the natural log of 2x to the fourth. Right, that was the u times v, minus, and then 8. And then first I'm going to do just the primitive antiderivative, right, the basic antiderivative here. And we saw this earlier, right? The integral of x to the negative half is x to the positive half, and then times 2, right, times the reciprocal of the new power. And I simplify again, so this is 2 times the square root of x times, the natural log 2x to the fourth, minus 16, right? 8 times 2 minus 16 times in the x to the half, which again I can write as the square root of x. All right, so once again, this is called the primitive, or the basic antiderivative of our function, of our integrand. Don't forget to add, all. We're trying to represent all possible antiderivatives. This is an indefinite integral, so I'm not sure which antiderivative they want, right? So plus c, plus any constant would still work here. And there we go. This is it. Now, if you want to check, once again, I'm not going to do that like I did the first example, but if you want to check by hand if this is correct, take the derivative of this with respect to x and see that you get something equivalent to our original integrand. All right. All right, but what I'm going to do is just go to Desmos real quick and see, again, this is the same thing as saying the integral from some constant a to variable x, and then just replace x with some other dummy variable like t, the natural log of 2t to the fourth divided by the square root of t dt. Right? These are the same thing depending on my choice of constant, right? These would only differ by a constant. Now, obviously, I can't have this be 0, because, you'd have the square root of 0 down here. You'd have the square root of 0 down here. It's not defined at 0. So I'll just have a be 1. All right, I'll just do 1. And then we'll see the graph of this, and then put this in plus some constant. You'll see the graph of this in the box is the same exact shape as the graph of our integral here, the graph of our original expression. So I got the integral from, so let's go y equals the integral from 1 to x of, and I'm changing this integrand here. We had the natural log of 2, and I'm using t, right? 2t to the fourth divided by the square root of t dt, right? Get rid of this. And again, I'll keep the CL. I keep the CS. Get rid of it. So there's our graph. There's the original integral as some curve. And I'll put in what we got. Y equals, our final result was 2 times, after integration, was 2 times the square root of x times the natural log of 2x to the fourth, right, minus 16 times the square root of x. And you'll see that has and then plus some constant, right? I'll put a slider in for the constant, but look at this. They have the exact same shape. They just differ by a constant, right? If I were to move that blue graph up, I could get it to match perfectly. Well, let's this up a bit. So, say c equals 0 to 50 or something. See, I could slide that graph up until they match. Right? They will perfectly match at some point. But as long as they have the same shape, the exact same shape, you've got the correct antiderivative, right? So back here, put in our answer. So I had 2 times, the square root of x. So that, in that case, right, the LIATE acronym worked, right? My log was the best choice of u there. So 2 times the square root of x times, the natural log of, maybe I'll put that in parentheses, times the natural log of 2x to the fourth power. Close that out. And then we had minus 16 times the square root of x. And then don't forget, right? Don't forget, plus some constant. All right, I'll put a capital C this time, but you could put a lowercase c, capital C, just plus some constant at the end, right? With these indefinite integrals. Wonderful. Yeah, and that's exactly how that put parentheses are in the log. They did not. Same thing. And again, please read through the answer explanations just to see where things are. All right. So I'm going to stop checking on Desmos. Okay, hopefully those first two examples gave you an idea as to how to check on the Desmos calculator if you're correct or not. Of course, you can always check by hand, right? Take the antiderivative you found, differentiate it, right? Take the derivative and see that you get something equivalent to the original integrand. All right. Now this time, look, see, this is a much easier objective. Use integration by parts to find indefinite integrals where you're given a u and a dv, right? So they're telling you what to use for u and what to use for dv. So these should be a lot easier, the problems from this objective. This time, I'll show you the table. I just realized I didn't show you the table again. Okay, this time I'll show you the table. I'll just do it straight away. So we have the integral of 2x times e to the negative 2x power, and then, times your differential of x. Okay, so they're telling us have u be 2x, and then have dv be the rest of it. So u is 2x, and then dv is the rest of it. So this is u, the rest of it is dv. Again, dv always includes the differential. So dv equals e to the negative 2x dx. Now, over here, I'm going to show you a shortcut for this. Now I'll do both, so it won't be a shortcut here. But here's what they call the table method or the tabular method. It's just a way of doing the same thing with less writing. So I put a diff, and then over here I'll put int. I like writing diff and int. Sometimes people will put this di, and you understand what that means. D is for differentiation, and then the integration column, all right, di, and then next to it, a series of pluses and minuses for each row. Now, we're not going to go down that far, okay? We're just going to have to do the first two rows, but a series of pluses and minuses for each row here. You can make rows if you want, just have like a row and a row and a row. You don't have to put the rows though. I see a lot of people do this without the rows, but I like it just to organize things more neatly. So yeah, so you start off here with your choice of U. All right, so these are like the U's here. And then you start over here with the dVs, right? You put U in this column, dV in that column. So U is 2x, and we said dV was e to the negative 2x. And you don't worry about the differential. Because this is the D column, you know the differential has got to be there, right? The dx. Okay, so this is how I would start this table method. Now, in the parts formula, integral of U dV is uv minus the integral of v du. So I want du and I want v. Right? So again, du, you differentiate the u statement. Right? U is 2x, so du would be 2 dx. And then dv, I integrate to get v. And v would be now the integral of e to the negative 2x would again be e to the negative 2x. But then remember this negative 2 here, I got to counteract that times negative half. Right, because when I differentiate this, I'd have to multiply by negative 2, so that would give me a positive 1 when I differentiate. Right? I got times negative half. Great. In the table method, and down this column, I'm just differentiating. So 2 here. And then down this column, I'm integrating negative 1/2 e to the negative 2x. So again, don't worry about differentials. Okay, so then when I'm filling this in, right, this integral should be u times v. So 2x times, and then v is this, negative half e to the negative 2x. On the table, you're starting up here, it's positive, and then you do a diagonal. You multiply, this would be u, and this would be v, just like this here, u times v. So I multiply these on the diagonal like this from left to top left to bottom right here. Down one, right one. So there's uv, then minus the integral of v du. So v is that half, sorry, negative half, e to the negative 2x again. And then du is just, 2 dx. So in the table method, right, you're kind of doing this little zigzaggy thing. We got uv, and then I'll do this in dotted, so you know it's a different thing. And then we're doing, this row here horizontally. You go diagonal, horizontal, diagonal, horizontal. So 2x times negative f e to the negative 2x, right? That's the uv. And then we're minusing the integral of this product here, right? So the diagonal is a product, and then you subtract, see that's why I got the minus here, minus this integral, the product of this integral, or sorry, the integral of this product, minus the integral of this product. Okay, then after simplifying a tad, all right, we get, simplifying 2 times negative half, negative 1x to the times e to the negative 2x. And then here, negative half times 2 is, negative 1. When I pull negative 1 out, that'll be plus 1 times the integral of e to the negative 2x dx, right? And we can integrate this, no problem. Right, now, I'm going to go to the table method and show you how we can do this also. But after integrating, we get negative x, right, times e to the negative 2x. And then when I integrate e to the negative 2x, right, that'd be e to the negative 2x times negative half again. So I have plus negative half, so minus a half, e to the negative 2x again. And then, of course, don't forget plus any constant. Right. Okay, so there it is. Right. Now, this table method, and I start with u and dv in the first row. Then I integrate the right column, differentiate the left column. If int, if int. Well, look what happens if I keep doing this. Keep differentiating down the left side, 2x, 2, and then eventually it's just a bunch of nothing. We're going to stop after the third. Once you get to 0, when I go horizontal and talk about, integrating, we'll be integrating 0, so there's no point in going on. So the rest of these zeros I just wrote were kind of meaningless. So I differentiate down this column, and then again I integrate down this column. So integrate e to the negative 2x, so e to the negative 2x times negative half, and then I integrate this again. So this would be e to the negative 2x, times another negative half. But negative half times another negative half would be positive 1/4. And then watch. Start going down the diagonals here. Right? So from this table method, we're getting 2x. So positive 2x times, and then this negative half e to the negative 2x, okay? And then we'd have minus this product, right? If I were to do integration by parts again for some reason, and we'll see examples later where we're going to have to do it more than once. I'd have minus this parts formula, so minus uv, right? I'd have minus uv. And then if I minus that, I'd have to plus an integral. That's why I got the plus in the next row here. You'd be adding the integral of this product. And then if I were to apply minus again, that's why they got this little plus minus here. Because if I repeat parts, I'm distributing the minus over the parts formula. So you got minus the first product, then plus an integral. And then I do it again, you'd have plus the first product minus an integral, and so on. So then I have a minus this uv, right? If I did parts again, this would be uv, this diagonal product. Minus, and then 2 times this, right? So 2 times this diagonal product here, 1/4 e to the negative 2x. And then I'm at the next horizontal where I would be adding this integral, right? The horizontal would be an integral. I would be adding the integral of 0 times this, which would just be 0, right? This would just be 0. So plus nothing. I could write that plus 0 here, but that's meaningless. So here we go. This is our primitive antiderivative. Multiply this out. This would be negative x, e to the negative 2x, and then minus, a half, e to the negative 2x, and then, that's exactly the same, again, before the plus c, right? That's exactly the same as what I got earlier. Negative x, e to the negative 2x minus half, e to the negative 2x, right? Exactly the same. And then, of course, don't forget your plus some constant at the end, right? For every general antiderivative, right? Yeah. Okay. So I'm going to actually keep doing this table method, right? Maybe for the next couple of examples, I'll do both until we get the hang of it here. Maybe you can, if you don't like the table method, right, you can always write this out. And the reason this is good, though, this tabular method or table method, is if we ever have to do integration by parts more than once, maybe you do uv minus v du, and then this integral of v du, if that integral's messy as well, I might have to do parts again for that integral. So yeah, so I'll keep doing both for a little bit, and hopefully you come to the realization that this table method is real nice. We'll save a little writing in the long run. All right, so back here, right, I'm not going to check on Desmos this time, but if you want to check by hand, differentiate your antiderivative, hopefully you get, 2x times e to the negative 2x back. Yeah, so we had negative x, right, times e raised to the negative 2x power, and then minus 1/2 times e to the negative 2x power. And don't forget your plus some constant, right? Plus any constant for these indefinite integrals. Right, wonderful. So they factored out the e to the negative 2x, right? You might notice that both of these terms have e to the negative 2x in common. They factored that out. But still, what I have written is equivalent to what they have written, so they gave it to me. As long as it's equivalent, we're good. Wonderful. So here's another one where they're giving us u and giving us ev. So let's do that. Once again, I'll do both. I'll write up both. You don't have to write up both, but I'll do the regular way and then the table method that I showed you. So we got the integral of 6 times the natural log of 7x to the 6th divided by an x to the 7th, and then you have this, new x in the numerator, right? Remember, the differential is always in the numerator. Okay? And they're telling us to let u be the log function. So the natural log of this, 7x to the 6th. They're telling us to do that. And then dv is the rest of it. So 6 over x to the 7th would be left, times dx. Which I would prefer to look at this as 6 times x to the negative 7th. Right? I'll look at it that way instead. Now, if I'm making my little table, or you do the table method. So again, I got my diff column where I'm taking derivatives. Got my integral column, right? Again, you can put just d and I. I've seen a lot of people do that. And then a bunch of pluses and minuses, alternating, plus, minus, plus, minus. You don't have to go too far. A lot of these you won't have to do integration by parts more than once or twice. And then I personally like separating the rows. You do not have to separate the rows if you don't want, as long as you keep things nice and in line. Right, so down here I'm putting, in the first row, I put the u and the dv, and don't worry about the dx. Right? You know the dx has got to be there. So natural log 7x to the sixth right there, and then 6 times x to the negative seventh right there, right? Again, without the differential. So now I'm going through parts over here, right? Remember, we differentiate the u to get du. So we have du will be, 1 over 7x to the sixth, then times the derivative of 7x to the sixth, right? Chain rule. So 42x to the fifth, and then times your dx, right? And when I simplify this, 7 goes into 42 6 times, and then 5 of these x's go away. So I'll have 6 over x dx. There's du. So yeah, back here, if I differentiate this, right, this is just 6 over x, or 6 times x to the negative first. And you can write that as 6 times x to the negative first as well. And then if I want v, right, I got to integrate the dv line. So v, you remember you raise the power by 1 when you integrate, when powers of x, powers of the variable, x to the negative sixth, and then times the reciprocal of that new power. So you'd have 6 times negative 1/6. So that'd be negative 1. That's it. This would be 6 times negative 1/6. So negative 1. So yeah, when I integrate here, right, this would be negative, x to the negative 6, right? Or negative 1 over x to the sixth, whatever. So now for the parts formula, right? I'll write it up again. Integral of u dv equals uv minus the integral of v du. Right. Just filling stuff in over here. So, yeah, so this integral should be u times v. Right. They told me u was this thing. Right, the natural log of 7x to the sixth. And then times v, right, times v, this is v, negative x to the negative sixth, right, or negative 1 over x to the sixth. There's uv minus, and then the integral of v, negative x to the negative sixth, times du, right, and this was du here. Now I'm going to write this as 6 times x to the negative first, okay? 6 over x, 6 times x to the negative first, and then times your dx, right? There's du. All right, so after simplifying a tad, this is, negative natural log of 7x to the sixth over x to the sixth, right? If you want x to the negative sixth with positive power, it'd be 1 over x to the sixth. And here I got minus, and then there's a minus in here, minus 6 actually. Well, actually, you know what? I'll keep the 6 in there. So pull the minus out to be plus the integral of 6 times x to the negative 7, right? Because we did that earlier, dx. And then finally, our uv is the same, negative natural log of 7x to the sixth over x to the sixth. And then this antiderivative, right, we saw earlier was x to the negative 6, times negative 1/6, which would make this minus 1. So the plus, minus x to the negative 6. So minus 1 over x to the sixth. Right, it's just this thing here. This integral we saw earlier, 6x to the negative 7. And then, of course, that's called the primitive or the basic antiderivative, and then plus any constant should work. And if you want to check, right, differentiate this with respect to x, and you should get something equivalent to this initial integrand back. All right. Now, if you're doing the, tabular method, you could keep going, but I don't see the point in it because, again, you should really, really stop when you realize the integral is going to be doable. So like first I'd do this product here. Right, so we'd have positive this product, right, the diagonal, natural log of 7x to the sixth times, and then, negative x to the negative sixth. And then if you think about the horizontal here, remember the horizontal, you're integrating that product. So minus, and then if I took the product of these, right, it'd be plus, right, because you have negative, negative. So plus the integral of 6x to the negative 7th. And that's something I can do. So I would stop there and forget the rest of, forget, I wouldn't continue on because I realize that this product is very integrable, right? So when I do the horizontal and look at that product, I can very easily integrate that product. So then I'd go, minus this integral, so plus the integral of 6x to the negative 7th. And it basically ends up being the same thing, right? We get the same crap that I did down here. So as you're working through the table, right, you do diagonal products, that's your UVs, and then horizontal products is what you're going to be integrating, right, minus the integral of E du. And if that horizontal product in a particular row is easy to integrate, I would recommend just stopping there, right, writing that integral out and taking it, right? That'd be a lot easier. All right, and then let's enter this. All right, so this is, we said negative natural log 7x to the 6th divided by x to the 6th or times x to the negative 6th, right? And then after that, minus 1 over x to the 6th. Now, because they're both over x to the 6th, I could have put them together, they have a common denominator, and then, plus some constant, right? Don't forget indefinite integrals, plus some constant at the end. Cool. Yeah, so see, they put them together. In fact, negative, that they put them together. Same thing, though. All right, moving on. So here's a case where we're gonna have, it's in the objective title. We're gonna have to use integration by parts more than once to find indefinite integrals. Okay, so got this integral of, now this is the natural log of x, times the natural log of x. It's natural log of x, to the second power in the numerator. And then we have, to the 5th in the denominator. So it's 1 over x to the 5th and then times dx. So I'll write this out. Again, I'll do it the regular way, and also I'll show you that tabular method. I'll do the tabular method separate this time, though. I'm not going to do them at the same time, or I'll write the table after. All right. So the integral, got this natural log of x, that whole thing being squared, divided by x to the 5th times dx. All right, so this time they're not giving us a choice of u or a choice of dv. All right, so we got to play around with this. Now, if you want to try that whole Liate thing, I'm seeing logarithms here, and it's this logarithm squared. That's the ugly part of this, right? If it were just 1 over x to the 5th, that'd be no problem. But it's this logarithm that's, throwing me up, throwing me off. So I'm going to start off by doing that. Let's have u be this logarithmic expression in the numerator here and see where this takes us. Again, if this takes me to a bad place, I got to start over and make a different choice of u. In fact, I do see a better choice of u here. It's neither here nor there. Let's see where this takes us, okay? All right, and then dv, remember dv is the rest of it. So if this numerator is u, then 1 over x to the 5th dx, right, would be the dv. which is x to the negative fifth. Okay. I want du. So again, parts formula, once again, integral of u dv is uv minus the integral of v du. And you know what? Since we're going to be doing this more than once, as part of the objective title, I'm going to call this u1 and v1. All right, so u1 be v1, and then the next time we'll have u2 and v2. Okay. All right, so du1, power rule first, it'd be 2 times the natural log of x, and then times the derivative of the inside, right, chain rule, which is 1 over x, right? So then times your dx. Okay, so 2 natural log of x to the first, and then times 1 over x. So 2 log x over x. Yeah. And then integrate, right? So I differentiated to get du1, and to get v1, I'm going to integrate. So v1, the x to the negative fourth. So 1 over x to the fourth, right? X to the negative fourth times negative 1/4. Right, so negative 1 over 4 x to the fourth, right? That's negative 1/4 times x to the negative 4. Okay. So now going through the formula here, the integral I started with is equal to uv. Right, so u1 v1, right? Right now I'm using u1 and v1. So u1, that was that natural log of x squared, times v1, right, this thing here. So negative 1 over, 4x to the fourth, or negative 1/4 x to the negative fourth, minus the integral of v1 du1. And again, I'm using ones here because this is our first step, our first time using parts. So integral of v, right? So again, v1, our v here is negative 1 over 4x to the fourth. And then du, right? Our du for this u1 is this, right? So times 2 natural log of x over x, and then you got your times dx, of course. All right, so simplifying a bit, this is a negative natural log of x squared over 4x to the fourth. All right, we got that in the denominator. Okay, so that's good. And here, if I'm gonna pull out some constant factors here, you have negative 2 over 4, that's negative half. I pull that out, that's plus a half, minus negative half, times the integral of, you'd have, if I got rid of the constants, again, negative 2 over 4, I'd have natural log of x in the numerator now, divided by, and then x to the fourth times x to the fifth in the denominator. Right. So great so far. I got this. Now notice this is better than the original, right? Look at this integral here. Right. Now I'm going to focus on this integral right here, right? After the half, right? We're going to multiply, when we find it, we'll multiply it by a half, right? Distribute a half. But now I'm doing this one, right? And look at this one compared to the first one. So the first one was basically the same thing, but power on log was higher. This is natural log of x, to the first. So this is better, right? This is much better. Now, if I ended up with, say, natural log cubed, I'd think, ooh, something's not right here. Maybe I have to go back and make a different choice for u and v. All right, so again, do this one, by parts, right? It's another product of two different kinds of functions. You have a natural log, and you have a power function, right? Times x to the negative fifth, 1 over x to the fifth. So again, that's usually a good indicator that parts will be a good choice of method. So if I'm doing this by parts, now this time, again, just ignore all the stuff before this, right? I'm going to cover it up. I'm just doing this integral now. So now I'm doing parts. So I'm going to call this, U2, right? Because I already did it once before. I'll call this U2. And again, if I'm doing the whole Liate thing, that might work, right? Try natural log, right? Just natural log of x. And then dv2, right? Again, the second dv, second v, is the rest of it, the x to the negative fifth dx. So like earlier. Okay. Then I differentiate, right? I got my parts formula up here still. I need u2 v2 minus the integral of v2 du2. I need u2 du2 would be the dx over x. All right. It's 1 over x dx, easy. And then, so yeah, you differentiate, do that, and then you integrate, right? You get v2. V2 is negative 1/4 x to the fourth. So negative 1 over 4x to the fourth, right? We saw that one earlier, right? And so now this integral should be u2 v2, so negative natural log of x over 4x to the fourth, right? That's the product of these two things, u2 v2, then minus the integral of v2 du2, v du, which would be negative 1 over 4x to the fifth dx. I have to multiply these. You have 4x to the fifth in the denominator. And this is way easier now. All right, notice now there's no log at all. Look at this, no logarithm at all. So putting this back into my original thing. Negative natural log of x squared divided by, 4x to the fourth plus a half of, okay, notice no integral here. I'm putting brackets or big parentheses. Half of the value of this integral, which we have this, and that's, negative natural log of x over 4x to the fourth, and then plus a quarter. Well, this ends up being negative, but plus a quarter of the integral, I pull this minus quarter out, of x to the negative fifth dx. Close the brackets on this. Sorry, the words by parts are in there, but okay, and we're doing half of all that. And that last integral is easy to take, right? It's just the integral of a power, and we've seen it a bunch already. We've seen the integral of x to the negative fifth a couple times now. So this is negative natural log of x squared over 4x to the fourth plus half of, big brackets, big parentheses, whatever, negative natural log of x divided by 4x to the fourth. And then remember, this integral of x to the negative fifth is negative 1/4 x to the negative fourth times the quarter here will be minus 1/16 x to the negative fourth. So that's 1 over 16 x to the fourth, right? This integral. And then finally, this is our primitive antiderivative. Don't forget to put, for indefinite integrals, plus any constant. So I could type all this in. What I want to do now, though, is distribute the half. So what I'm going to type in is this, negative natural log of x, right, that to the second power, divided by 4x to the fourth. And then when I distribute the half, that'll just multiply these denominators by 2. So then we'll have plus, this negative log x over 8x to the fourth. And then plus a negative again, so minus, and then 1 over 32x to the fourth. And then again, don't forget plus any constant at the end. So this should be good. Now, if you want to get a common denominator and put them together, that's fine too, but this should be fine. And if you want to test it, right, take the derivative of this, see that it's equal to the original expression we had, the original integrand. Right, so that's one way of going about this. All right. Now, I'll show you that the table method would be kind of a pain here. I mean, I said it would work, it helps you set things up. If I was doing a table for this, right, so we have the integral again of this natural log of x squared over x to the fifth dx. If I was doing tables with this, if I was doing the table method, so again, I got the diff column, I got the int column. I'll make these bigger. And then rows of pluses and minuses, alternating plus and minus, right? We're not going to have to go that far, hopefully. And again, me personally, I like separating the rows. Now, if I made that choice of u and dv that I did in the last page, or the beginning of this example, right? U was natural log of x squared, dv was x to the negative fifth dx, so I'm just writing x to the negative fifth over here. Start differentiating. First I'll differentiate. This is you know, 2 natural log of x, oops, ln, and then divided by x, right? 4 times x to the negative first. This here, right, we've seen a bunch of times now, negative 1/4 x to the negative fourth. Now, if I were to do the whole, again, think about every row I make, I'm going to think a little bit about whether or not the integral would be good. So I'd take this product, that'll be part of the antiderivative, and then I think about this product in this row, and could I integrate it pretty easily? Well, now if I multiply these, you'll have x to the negative fifth, right? So I'll write this as 2 natural log of x times x to the negative first, right? If I multiply these, I got x to the negative fifth, but I still have this log x attached. So I'd have to continue on. Uh, and something you could do is, you're integrating this product here. If you realize, ooh, it would be easier to split, put power, separate, get things together with the other functions that are like themselves. Powers with power functions, logs with logs, trigs with trigs, crap like that, exponentials with exponentials. It might be beneficial to take this x to the negative first and just put it over here with this. Because look, if I kept it the way it is, if I kept it the way it is and had to differentiate, I'd have to do the product rule here. This would be 2 natural log of x, times, and the derivative of this would be negative x to the negative 2, right? And then plus, and then x to the negative second, sorry, 2x, x to the negative first alone, then times 2 over x, so it's plus 2. And then I integrate this, this would be x to the negative 3 times negative 1/3 be positive 1/12 x to the negative 3. And if I were to multiply these, right, so I mean, yeah, you could do this product next, right? This diagonal product would be in the antiderivative. But then you look at this product, the horizontal, look at the row. Sure, one of these is good, but then the other one would end up having a natural log x to the negative fifth again. You'd be kind of stuck in this like cycle of natural log x to the negative fifth. So yeah, so a better method. So again, I know it's tough to. There's a lot. Like I mentioned it. I mentioned way early on. Integration is an art. Integration is an art. Sometimes you got to think about little creative moves to make. So it might be beneficial, like I said earlier, to move this, right? Take a factor from the diff column and multiply it, put it in over here, turning this into -1/4, x to the -5th, and then that'll get rid of this, and now I have just 2 log x, right? This is after taking this product, like, just, ugh. So maybe the table method isn't always the best, right? After this, then you do that, right? After. So I'd have, natural log of x squared times the -1/4 x to the -4th, right? Because it can't be this x to the -5th. You saw the final result. And then I do some shifting. Fine, minus this integral, because it's only after you do uv minus the integral of v du, right? So you're doing the uv first, and then the integral. Then I look at the product in this column, in this row, and can do the shifting. Okay, then I can do the shifting. I hope that makes sense. And so then, I would do this again. 2 log x, the derivative is 2 over x, so 2x to the -1st. And then integrate this, which would be positive 1/16 x to the -4th, right? And then you're doing this product. So the 2 log x, right? This is the u now, and this is the dv. I know it's a lot to focus on. Maybe it would be best if you just did the other way. There's too much manipulation going on here, I feel. But it's still doable. I know it's annoying, but it's doable. So then I do this, minus this uv, so minus, 2 log x times the 1/16 x to the -4th. And then look at this final row here, right? This third row, I'm gonna look at the product of this and this, 2 and this, that'd be 1/8 x to the -5th, and I can integrate that. So we add on, right? Plus, it's alternating, plus this integral. And so plus the integral of 1/8 to the -5th dx, and then this becomes, you know, -1/32 x to the -4th, and then you're good, right? So it's this product plus that plus some constant at the end. And that would be exactly the same thing I got earlier. But yeah, it still works. You just got to remember to do your UV product before you start looking at the row, right? You do your diagonal product, do UV, and then look at the integral, look at the row, see if it's integrable. And if it's not nice and integrable, maybe you can manipulate junk. Um, yeah, so I mean, this is exactly the same as earlier. So if that's not confusing enough, sorry about that. That was a jumbled mess. But, just again, do the UVs first, and then look at the row in the table. See if we need to do any shifting of factors. Now, set at the top of this example, I thought I saw another choice of u and dv that would be better. So again, the Liate not always perfect. I mean, this is still gonna adhere to the Liate model, but let's try this another way. So I was given the integral of, the natural log of x. Now that was natural log of x squared. All right, so I'm going to do this. All right, this is something I saw here. This is natural log of x times, and then natural log of x. All right, that's the same thing as the natural log of x squared. Right? And then down here I had x to the 5th. You might think of that as x to the 4th times x, right? That's x to the 5th. And then times dx. So here's what I'm going to do. Oh, you know what? Maybe this won't be great. Yeah, that won't be that good. actually. All right, so I little hubris here. I thought I could do this better than the original choice, but yeah, I was gonna have this be dv because I know how to integrate it, but then I didn't really think about the u. Right, dv. If I had dv be the natural log of x over x dx, right? That's integrable. Because if I let u be natural log, then this would just be du, and I'd get 1/2 u squared, right? This would be a half of the natural log of x squared. But then this would have to be u, though. All right, this would have to be u. I didn't think about that. My apologies, right? Because when I do uv, I'd have natural log. When I do u times v, I'd have a natural log of x cubed. But then when I differentiate this, there'd still be a log x in there. Right, there'd still be a term with a log x, and then when I multiply it by v, when I do v du, there'd be a natural log of x cubed, and that would raise the power by 1. Okay, so this is a bad choice. So my choice initially, where we just separated the logs from the powers, was a much better one. Still, play around with it, though. That's all I'm saying. That's a bad choice. And that would end up being terrible. I'd actually raise the power on the natural log if I made the choice I made there. Again, just a good lesson for you. I thought I could do it, but I was wrong. Right. All right, so yeah, so finally after all that, right, this is what I'm entering. All right, so we have negative natural log of x squared, right, the whole natural log of x thing there squared, divided by 4x to the fourth, right there in the denominator. Right, then the next term, minus the natural log of x in the numerator divided by 8x to the fourth in the denominator. And then minus 1 over 32x to the fourth. And again, don't forget your plus constant, plus some c, lowercase c, capital C at the end. And this should be good. Great. Yeah, so they definitely had u be the natural log of x squared like we did earlier. Full. Now, of course, if you see a better substitution or a better choice of u to make, try it out. Right? You don't have to adhere the liate mnemonic all the time. So now we got another one where we're doing parts more than once. And so again, I'll call the u and v u1 and v1, and then we'll have u2 and v2. Yeah, so maybe the table method is really good when one of the factors of your integrand is a polynomial. I'll say that. The table method is very good when one of the factors of your integrand is a polynomial, because eventually, if you put the polynomial as the u, eventually, when you differentiate a polynomial, it'll eventually be 0. And then you can stop the integration by parts. So yeah. So in the last example, when I was doing the table method, right, it still worked. You just had to do a lot more manipulation than I think most people would be comfortable with. Okay. So here we're asked to take the integral of the cosine of, and then you have the natural log of 6x inside. Do this by parts. So the integral of, and then you have the cosine of the natural log of 6x. Okay, so this is not cosine times the natural log of 6x. Right? Natural log of 6x is the argument of cosine. It's inside. So I can't have u be natural log and then dv be cosine dx, right? Cosine of what, right? You got to have something inside the cosine to have it make any sense. So really the only thing I could have u be 1, and you could say this is times 1. I could have u be 1 Then I'd be just taking this integral again. So the only sensible choice here is to have this whole thing before the differential be u, and then just, 1 dx, just the differential, be the dv, if I'm going to do this by parts. And again, I'll call them u1 and dv1, right? u1 and v1, as they mentioned, and it's in the objective title, right? We're going to be doing parts more than once. So I'll have u1 be this cosine of the natural log of 6x, and then the v1 be just dx, right? 1 dx, just the differential. And again, parts formula, integral of u dv is u times v minus the integral of v times du. And all those are u1 and v1 at the moment. So if I want du, differentiating the u1 here, du1, now the derivative of the cosine of something is negative sine of that thing, right? So negative sine of the natural log of 6x, but then times the derivative of the thing inside. Now the derivative of the thing inside would be 1 over 6x, and then inside that is 6, so times 6. So 1 over 6x times 6 would be 6 over 6x, which is just 1 over x. All right, so I'm just going to over x. All right. And then, of course, times your dx, right? Times the differential of x. So that's du. And then I want v1, or just my original v. Let's integrate the dv. Now the integral of 1 dx would just be x, right? So v1 is just x. Okay. So I'm going to go through the parts formula. All right, the integral of u1 times dv1 is going to be u1 v1. Right, so this product here, u1 v1, so x times the cosine of the natural log of 6x. So there's u1 times v1. I wrote it v1 u1. It doesn't matter what order those come in, right? Then minus the integral of v1 du1, v du. Now hopefully you can see when I multiply these, the x's will cancel. You have x over x, so those will go away. And I'm left with negative sine of natural log of 6x. And because it's negative, I can pull that out, make this plus the integral of sine of the natural log of 6x. And then, of course, the times the dx. Okay. So I start off with the integral of cosine of natural log of 6x. Now I'm trying to evaluate the integral here. All right, do this now, and I'm going to do this by parts as well, because it's something I don't know. Right? It's not just sine of x, right? It's the sine of the natural log of x. That makes it incredibly harder. So again, I'm going to do it by parts again. This time I'll call it u2 and dv2. Of course, the only thing that makes any sense here is having u2 be this whole thing. Have dv2 be the differential again. So u2 is going to be the sine of the natural log of 6x. Sorry, I had to write the sine angle here. I forgot to leave myself some space. And then dv2 is just the differential, just dx. And so du2, right, the derivative of sine of something is the cosine of that thing. So the cosine of the natural log of 6x. And then times the derivative of the natural log of 6x, which would be, again, 1 over 6x times 6, just 1 over x. So just over x, and then dx. And then v2, right, I'm integrating this, would just be x, right? The integral of 1 would just be x. So I go through parts here. So I'll write the initial stuff, right? We have x times the cosine of the natural log of 6x, right? That's the beginning, plus And then this integral, just going to have it be, u2 v2 minus the integral of v2 du2. With all my u2s and v2s over here the second time I'm doing parts. So u2 v2, that'd be sine of natural log of 6x times x. So x times the sine of the natural log of 6x, and then minus the integral of v2 du2, v du. And again, when you multiply these two, hopefully you see the x's canceling again, x over x. So I would just have minus the integral of cosine of the natural log of 6x dx. So now we got this. Now you're probably thinking, we're back to where we started. Look at this integral here. This integral is the one I wanted to take in the first place. All right, the integral of cosine of natural log of 6x dx. Well, that's actually perfect. All right, so I'm going to write this all out in one big line here, all right, on this next page. So look at this. We have, here's the integral we started with. We have the integral of the cosine, the natural log of 6x dx. We're saying this should be equal to, you got this stuff here, right? X times the cosine of the natural log of 6x, right, that was this first term, plus x times the sine of the natural log of 6x, okay? And then minus the integral we wanted to start with. Wanted from the beginning, minus the integral cosine the natural log of 6x dx. So again, these are the same, right? This expression here and this here, these are the same thing. These things I just underlined. So if I want to solve for those, it's just like solving any other equation. Solving this equation, I've got like, if I had, all right, so this is a side note. If I was solving x equals some junk minus x, a little squiggly line here for some junk. If I want to solve, these are the same thing. This thing over here, and then I got x, the same exact quantity over here. Wouldn't I just add x to both sides and get 2x equals the squiggly junk, and then divide by 2 to get x alone, to get the thing I want alone? So it'd be the squiggly junk cut in half. So if you're seeing the same thing in different places and you want to solve for that thing, it's just like a linear equation, right? Get all the stuff with that thing on one side, and then get it alone. Make it divide by whatever coefficient you have. So yeah, so I'm gonna add this, right? This I'm gonna add to the other side, right? Because it's minus right now. I'm gonna add it. Get all the stuff with this thing I'm looking for to the same side, and that'll give me 2 of that integral. 2 of it, right? 1, and then I'm going to be adding, the coefficients right now are 1 and -1. I add 1 of it, so I'll be 2 of it. 2 times the integral of the cosine of the natural log of 6x dx equals, this stuff here before the integral. This is the squiggly junk I was mentioning. This x times the cosine of the natural log of 6x plus x times the sine of the natural log of 6x. And then finally, right, I have 2 of this integral. I wanted 1 of it, right? The initial problem was asking for the value of 1 of this integral, so I divide by 2. So the integral that we started with, right, the cosine of the natural log of 6x is, I could put a half in front of both of these, right? Times a half, divide by 2, same thing. I'm just going to put that whole thing over 2, though. Just x times the cosine of the natural log of 6x plus x times the sine of the natural log of 6x. All of this divided by 2, and there you have it. This right here is primitive antiderivative of the cosine of the natural log of 6x. And then, of course, if I want to describe every antiderivative, I could just then afterwards add on any constant I wish, right? Plus c. It's an indefinite integral. Never forget the constant of integration there. And there we have it. So you may see this, you may come across stuff like this with other problems, right? You try integration by parts once, great, you do it again, great, you do it another time, and maybe you have to do it a third time, fourth time. And while you're in the process of it, you see an integral that looks exactly the same as the one you started with. Then you can do it, just solve it just like you would any linear equation from algebra, right? Gather all that integral, all the terms with that integral on one side, and then divide by some constant, divide by some coefficient, and you'll get it. All right, so I'm going to type this in here. All right, so we had, all this in the numerator, x times the cosine of the natural log of 6x, then plus x times the sine of the natural log of 6x. All right, so all that divided by 2, and then plus some constant afterwards. Yeah, see, they just divided each by 2. I divide the whole thing by 2, but same deal. Same thing. Okay, so we're back to the objective, the easy one. We'll call it the easy one, where you're given a choice of u and a choice of dv, right? And then just going through the parts formula. Yeah, so this one here, this is where I would highly recommend, if you want to save some time, do the table method. Right? I told you, if one of the factors of your integrand is a polynomial, like negative x here, the table method, if I put that in the differentiation column, you'll eventually get down to 0, which is real nice. So this one, because one of the factors, the u they're giving me here is a polynomial, I'm going to do that table method. All right. So we have the integral of negative x times the cosine of 2x times dx, right? And if I make my table, right, again, there's a differentiation column, there's an integration column, and alternating pluses and minuses. Just a few rows should cut it. They said let u be, the negative x, and then the rest of it, right, be the dv, cosine 2x dx. Well, that's here. We go negative x in the differentiation column. That's where my u goes, and then the dv cosine 2x. Again, don't worry about the differential. Right. And then when I differentiate, see, this would be negative 1 and then 0. Like I said, if one of your factors of the integrand is a polynomial, that would be a pretty good choice if you're trying this table method here, because again, eventually, all right, the derivatives end up being 0. And then hopefully the stuff in the other column can actually be integrated. Right? If you have a polynomial times something that you don't know how to integrate, then this won't work. Lots of caveats, right? Lots of restrictions. All right, and then when I integrate, start integrating cosine 2x, this would be sine of 2x, but then times a half, right? To counteract the 2 in there. And then integrate one more time. This would be negative 1/4 cosine 2x I just want to get down to this row with the 0 in it. And now we do our product. So here's the first UV. All right, so this is going to be equal to positive, you have plus negative x times a half sine x. So negative half sine of 2x. That's my first UV. And then you'd be subtracting this product, doing this integral, the integral of positive 1 negative times negative half sine of 2x, which I know how to take. But if I just go to the next, do this next diagonal product here, right, we do minus this product. Minus this product, which would be minus a quarter cosine 2x. And then when I look at that horizontal row, right, when I look at that row, we'll be adding the integral of this product, but this product is 0. So I'd have plus 0 and be done with it. So there it is. And then don't forget to add any constant at all. Okay, so again, very, very quick and easy with the table method. If one of your factors of the integrand is a polynomial, and the other is something you can actually integrate, right? That's the caveat there, right? It's got to be something you can actually integrate to call it dv. All right, so I'm going to enter this, and again, if you want, double check, take the derivative of this expression. You should get, something equivalent to the original integrand back. So negative 1/2 times the sine of 2x minus 1/4 times the cosine of 2x, right? And then plus any constant. Ooh, did I mess up? Ooh, well, hopefully they give me another chance here. Okay, let me go back to my page. Oh, yeah, I forgot the x. Ah, I just put negative half sine of 2x, but I forgot the x in the first product. Hopefully you caught that, right? There should be an x in that first term. So everything else is fine, right? Negative x, so positive this product, so minus half x sine 2x, and then minus this product, which would be minus a quarter cosine 2x, and then, plus nothing, right? Plus the integral of 0. And then add any constant to that. So I forgot the x for the sine of 2x. So let me go back here and fix that. Sorry about that. There we go. All right, gave me another chance. I can move on now and live. Wait. All right, so once again, here's another one where, see, they give us a u, they give us a dv. All right, so this should be pretty simple. And once again, the u is a polynomial. All right, so because the u is a polynomial, I'm just going to do that table again. All right, that tabular method, table method. And this is actually pretty similar to the last example. So we have the integral negative 2x times the cosine of 4x dx, right? And they're telling us to have u be negative 2x, right? And have the dv be the rest of it, the cosine of 4x dx, right? So again, because this is a polynomial, I'm going to like the table method. So I'll have my differentiation column and then my integration column, alternating pluses and minuses for each row. Should only need 3 of them. And then yeah, u goes in the differentiation column. And then the dv, again, don't worry about the differential, right? You know that it has to be there, goes in the integration column. And then I differentiate. Now this would be negative 2 and then 0, right? Eventually you get down to 0 when you have polynomials in that differentiation column, which is great. And then I can integrate cosine 4x, right? This would be a quarter times the sine of 4x, and then negative 1/16 if I integrate one more time times the cosine of 4x. All right, and I'm down to that first row with the 0 there. And we can get all our u, the first time I do parts, there's my first u times v. So this will be negative 2x, and I won't forget the x this time, times a quarter sine 4x. That'll be negative 1/2 times x times the sine of 4x. I didn't forget the x that time. And then my next uv, if I did parts again for some reason, This would be the next UV, but I'd be subtracting that, right? So minus this product, positive 1/8, so minus 1/8 times the cosine of 4x. And then if you look at that last horizontal row, where you're adding this integral, the integral of this product, you'd be adding on the integral of 0, which is 0. So plus nothing. So there we go. This is it. This is our primitive antiderivative. And then you add on any constant to that, and it should still be all right. And another antiderivative. There we go. So I'm going to enter that. So we got negative 1/2. Again, this time I can't forget the x, right? Times x times the sine of 4x. And then minus 1/8 times the cosine of 4x. And then plus any constant. All right, let's see. Great. All right, so that objective's done. Only 2 hours in. So yeah, okay, look. Integration by parts to evaluate the following indefinite integral. All right, so look at this. X to the 7th times e to the 3x to the 4th power. It's a polynomial times an exponential. Now, you could take the polynomial all the way down to 0, but this integral here, if I had just e to the 3x to the 4th power, I don't see how to integrate that, right? And actually, e to the 3x to the 4th would be one of those that can't be expressed as elementary functions, as I said at like the top of the video. E to the x squared, e to the x cubed, e to the x to the 4th. Anything with a power of x in the exponent higher than 1 on its own can't be expressed as in terms of the elementary functions. All right. So let me pull this up. Yeah, so remember earlier I said, oh, if a polynomial is a factor of your integral, might be a good choice for you, but you know, the that exponential though on its own is real rough. So maybe I could do a u sub here first. Let's check that out. Perhaps we can combine u subs. So I'll do this a couple ways, right? Just to show you the art of integration. There's usually more than one way to go about doing these things. So I have x to the 7th, times e to the 3x to the 4th power, and then times your dx. I would much rather have e to something to the 1st power and the 4th power. So I'm going to do a u sub first. And you know what? Because I'm going to be using u's again later for integration by parts, let's do a different letter here. Let's call it a t sub. Okay. So instead of e to the 3x to the 4th, I would much rather have e to the t. I'm going to have t replace this 3x to the 4th. And don't forget though, when you make replacements, I want to rewrite this integral in terms of this t now, so I need to get rid of the dx as well. I need a differential. So dt, right, would be the derivative of this, 12x cubed with respect to x, and then times dx. Okay. Now, so dx, right, I can write dx as dt divided by 12x cubed. I know that still has x in it, but you'll see after a bit that all the x's will go away after I make these substitutions. All right, so if I make these substitutions, we got the integral Keep this as x to the 7th for a second, times e to the t, right? 3x to the 4th is t. And then I said dx was going to be dt over, 12x cubed. And you see, now this is not good. This is not good yet. Right? I want to be totally in t, no x's. But I see some x's canceling here, right? X to the 3rd will go away, and then this x to the 7th becomes x to the 4th. And I'm going to pull the 1/12th out. Okay, so this is 1/12th integral of, now I have x to the 4th times e to the t dt. It's still a problem, right? I want to be in the t domain, right? I don't want to be in x at all. But where did I see x to the 4th earlier, or an x earlier involving t? That's from my substitution line. See how x to the 4th, right, is just 1/3 of t. It's t over 3. So that can replace this x to the 4th here. And if I do that, this would be 1/12th times the integral of t divided by 3 times e to the t, right, dt. And then I can pull the 3rd out. So it would be 1/36th times the integral of t e to the t dt. And this is a lot prettier, I feel, than the original, where the powers on the variables are 7 and 4. And here, the powers on the variable t, the independent variable is now called t, is first powers. A lot easier to work with first powers than 7th powers and 4th powers, in my opinion. But now I'm going to work with this integral. And whatever we find here, we're going to multiply by, 1/36th. All right, so here's where I'm going to do parts. You see I have, again, a polynomial in t times some exponential function in t, so I'm going to do parts here. So now I'll have u be t, polynomial, and then dv be the rest of it, the e to the t dt. That's something I can integrate pretty easily. Right? It's not e to the t squared or e to the t cubed, right? Those would be impossible in terms of elementary functions. And remember parts, so write the parts formula up again. The integral of u dv equals uv minus the integral of v du. Okay, so I need du. Du is just 1 dt with respect to t now. And then v, when I integrate this, would just be e to the t. Easy enough. So this is 1/36 times, again, big set of parentheses now. I'm actually doing the integral. uv, and multiply u and v, p e to the t minus the integral of v du. So these two, right? 1 e to the t dt. So just e to the t dt. And that's an easy integral to take, right? That would just be e to the t. It's like e to the x dx or e to the y dy, right? It's just e to the t. Okay, so this is 1/36 times, quantity t, e to the t, minus, and then that integral is just e to the t. All right, and I'll throw the constant on the end when we're totally done. But this is not totally done yet. All right, going back up. Where my original integrand was in x, the x world, the x domain. My answer is in this new t world or t domain. But I want to make sure, if I'm given something in the x world, the x domain, I would like the answer to be in the x domain as well. I don't want to leave worlds. So, sub back. We've got to sub back. And remember what t was, right? Remember I said here, t was 3x to the 4th. And I'll distribute the 1/36th as well. So we have 1/36th times t, which is 3x to the 4th, times e to the t, right? E to the 3x to the 4th power. minus e to the t, sorry, minus 136th, distributing the 136th, e to the 3x to the fourth power. And then if I simplify a little bit, all right, 3 times 136 would be 1/12. So we got 1/12 times x to the fourth times e to the 3x to the fourth power, and minus 1/36 times e to the 3x to the fourth power. There you go. This is the primitive antiderivative of our original integrand. And you can double check by, taking the derivative of this, see that you get that back. And then, of course, you want all the antiderivatives, so plus some constant, right? Always, always, always on these indefinite integrals, plus some constant. Whew. Okay. So this just goes to show you, you can mix up methods, mix up techniques. I have to do a U sub or T sub or M sub or whatever letter sub you want, right? I called it T because I knew later I was going to use U for when I did integration by parts. Or I could have called that U1 and then later, U2 or something, or U0, whatever. Now, you could have also done this without doing a substitution initially. So let me try this again. Again, I might be totally wrong, but let's play around with it. So say I start with this again, and I broke this up, right, into the integral of x to the 7th. Now, because I know the derivative of 3x to the 4th is going to involve x cubed, you break up x to the 7th, to x to the 4th times x cubed. And then we have the rest of this, e to the 3x to the 4th dx. And then this is something I can actually integrate. The x cubed e to the 3x to the 4th, again, because the derivative of x to the 4th involves x cubed. So now I'll have u be this polynomial here, u be x to the 4th, if I'm doing parts. Maybe I'll call it u1. And then I have dv1 be the rest of this, right? X cubed times e to the 3x to the 4th power, dx. All right, and then, you know what? I won't need to do this twice, so just call it u. U equals x to the 4th. And then du is 4x cubed dx, and then v, right? Remember, this would be e to the 3x to the 4th power, right? The derivative of this would be 12x cubed. So I need to multiply by 1/12, right, to get rid of that 12. And then I'd have the derivative of this was my original. Right? So then this integral is, uv, so 1/12 to the 4th times e to the 3x to the 4th power, and then minus the integral of v du, like the horizontal thing here, minus this product's integral. Now 4 times the 12th is a third, right, so I pull a third out, times the integral of, and then you have x cubed times e to the 3x to the 4th power, and I did that integral earlier, right? That was my dv earlier. So this would be minus 1/3 times, 1/12. Right, this integral is 1/12 e to the 3x to the 4th power. And then there's your minus 1/36, right? I got that earlier. So this is exactly what I got earlier. All right. So you didn't really need to do a sub there, but it was probably harder to see. But there's your 1/12 x to the 4th e to the 3x to the 4th power. And then minus 1/36, negative 1/3 times 1/12 e to the 3x to the 4th power. And then, of course, plus some constant out there. All right, so this is what I shall be entering. Right, so 1/12 times x to the 4th times e to the 3x to the 4th power minus 1/36 times, just e to the 3x to the 4th power. And then, of course, at the end, indefinite integrals plus some constant. Okay, great. All right. So here we have an inverse trig function. Now, in Calc 1, you didn't see integrals of inverse trigs, so I'm not going to have that be part of the dv. It's going to be part of the u, and I have to maybe hopefully I'll refresh your memory. Remember, so let's recall here. You know what? I'll just make a little chart with some of the inverse trigs, right? So f and f prime. So how about inverse sine of x, right? Or I'll say the inverse sine of u, right? It's inverse sine of something. That was 1 over square root of 1 minus u squared. If there was something in here, you'd multiply by the derivative of that, right, times u prime or whatever, but let's chain rule. Then remember inverse cosine was just the opposite of this, right? The derivative was -1 over the square root of 1 minus the argument squared. And inverse tangent was the derivative was 1 over 1 plus the argument squared. And there's inverse cotangent would be the opposite, inverse secant. Inverse secant was 1 over the absolute value of the argument times the square root of the argument squared plus 1, or 1 plus the argument squared. Or sorry, -1, -1. Apologies, -1. Does it be secant tangent? Yeah. And then the inverse cosecant was the opposite of this. Okay, so hopefully you recall, right, that's -1, not plus or minus, but just minus. So hopefully you recall your derivatives of the inverse trig functions. So when I'm integrating what they have here, we have the integral of the inverse cosine, right, or the arc cosine, right, ARC, you might see that. Inverse cosine of 8x, and then, dx. And if I'm just doing parts here, now you could do a u sub or a t sub or whatever if you want to get rid of the 8x, but that's just going to have that's just going to add a constant multiple onto this. No real biggie if I leave it this way. So if I'm doing parts, I'll have u be this and just this, right? And dv be the differential. Inverse cosine of 8x, and dv be the different, 1 dx. Then du, derivative of the inverse cosine of something, is -1 over the square root of 1 minus that expression squared. So that'd be 64x squared. Back to the second power, right? U is 8x here. Then times, this chain rule times the derivative of this. So times 8. That's just got to put 8 up top here. So -8 over the square root of 1 minus 64x squared, right, dx. And then integrate this to get v, right? That'll just be it, right? V equals x. All right, so parts formula, and the integral of u dv equals uv minus the integral of v du. I'm writing this every single time, it seems. So uv, take that product, right? So x times the inverse cosine of 8x. Great. Minus the integral of v du. Take that product. Now, there'll be a -8 here, so let's pull that out. Say +8. All right. And then we have x in the numerator and the square root in the denominator here. X over square root of 1 minus 64x squared. Right, and then your dx, of course. All right. And now I'm focusing on this integral. Right. This integral, once we find it, we're going to multiply it by 8. Notice in the square root down here, there's a quadratic polynomial. And the derivative of quadratic here will be some linear, and I've got a linear up in the numerator. So I'm going to make a nice substitution here. Now, because I already used u, I'm going to call it p. So in this integral, I'm going to have p replace this quadratic polynomial down here, 1 minus 64x squared. And then dt would be negative, do the power rule here, negative 128 times x dx. And you see the x dx here, there's x dx here. So if I divide by negative 128, right, this is going to be replaced with this x dx, going to be replaced with negative 1 over 128 dt. Right? And then this will just be the square root of t. Okay, so now I have, you know what, I'm just going to do that integral separately. So I'm taking this integral, doing it separately. We now have this, the integral of, negative 1 over 128, I'm pulling that out, dt over the square root of t after making all these replacements. And again, we'll multiply this by 8 when we're done. I'll just put the 8 there now. All right, so the 8's coming down as well. And this is just the integral of t to the negative half power, right, over the square root of t dt. And that would be t to the t to the positive half times 2. We saw that earlier in the video. And this is also being multiplied by negative, 8 over 128, and 2 goes into 128 64 times, and 8 over 64 is 1/8. So this is negative 1/8, t to the half, or negative 1/8 times the square root of t. And don't forget what t was. T was this 1 minus 64x squared. So this is negative 1/8 times the square root of 1 minus 64x squared. All right, there we go. That's this integral here. So when all is said and done, so finally, when all is said and done, our integral that we started with, so the integral of the inverse cosine of 8x dx is x, the original uv, x times the inverse cosine of 8x, and then plus this, right, this 8 times this integral, but we did all the substitution and found that this was minus 1/8 times the square root of 1 minus 64x squared. Right, and then that's it. There's your primitive antiderivative of the inverse cosine of 8x. Then don't forget, we want to represent every possible antiderivative. Right? The indefinite integral is always, plus some constant at the end. Right, so once again, we're seeing you might have to combine techniques, right? Integration by parts. And in the midst of that, I performed an integral where I did some sort of substitution. You can call it U substitution, T substitution, whatever letter you want, as long as you haven't used it before, substitution. All right, so let's enter this. So we got x, x times, let's see, they got the inverse cosine in here. Yeah, there's inverse cosine of x. Because I just don't trust myself to put the raised to the -1 there. It's not to the -1 power. Remember, that means inverse cosine. So x times the inverse cosine of 8x, and we had minus 1/8 times the square root of 1 minus 64x squared inside that square root, and then outside all of that plus some constant. Great. Yeah, So again, just to show you that you might have to mix up techniques, integration by parts, some sort of substitution, right? Right here with a U sub. I know they have multiple U's here. It's not wrong. I mean, you just got to make sure you're telling people, hey, I'm doing a different technique right now, so they can use the same letters again. But I personally, just for less confusion, try to use different letters or different subscripts to represent things. Okay. All right, so here's another one where we're asked to do integration by parts more than once. And I've seen plenty of these before. What you're gonna notice, right? This will be like earlier in the video, right? We did the integral of the cosine of the natural log of 6x, right? And remember in the process of doing integration by parts, we saw that integral again. And then we could gather all that integral, all the terms with that integral to one side and actually solve for it. This one here, where we have a mixture of an exponential with a trig, right, e to the 2x sine of 3x, this is going to be another one of the integrals like that, where while I'm going through the procedure, going through parts a couple times, I'm going to see this integral again. All right, so watch. All right, so we got the integral of e to the 2x times the sine of 3x dx. Okay. So if I'm doing the Liate thing, right, that mnemonic device, Liate, trigs come before exponentials. But I said earlier, you can kind of interchange trigs and exponentials when it comes to your choice of u. But I'll stick to the Liate thing just to help you out, because again, this whole introductory section here, it should be helping you out for most of these integrals. So I'm going to be doing parts more than once here, so I'm going to call this u1. Right. So my first u, I'm going to have be the trig function, the trig product, the trig factor, sine of 3x. And then v1, I'm going to call it v1, be the rest of it, the e to the 2x dx. Then we find du1, right, the first du, should be 3 times the cosine of 3x, right? Chain rule times 3, got a times 3 there at the end. And then the first v, right, v1, integrate this, it'd be half e to the 2x. Once again, the parts formula, integral of u dv equals u times v minus the integral of v times du. Right? So we're doing that for our first u's and v's here. So uv, so it's a half of e to the 2x times the sine of 3x. And then minus the integral of v du, right, minus this product here, the integral of this product, which will be 3 halves. You got 3 here and a half there. So minus 3 halves, the integral of e to the 2x times the cosine. Oh, yeah, sorry, I forgot the dx here. Sorry, du1 should be 3 cosine dx. And then you have e to the 2x cosine 3x dx. Okay. So now let's focus on this one here. Right, so I'm going to take this one aside, do it separately, and put it in here, and we're going to multiply it all by negative 3 halves, okay? So do this one separate. Now we're going to take this aside. Again, I have a nice product of 2 different kinds of functions, exponential and trig, so I'm going to try parts again. So again, if I'm sticking to the whole Liate thing, I'll do the trig. I have the trig be my choice of u. So this is my second u now, so I'll call it u2. Cosine 3x And then the rest of it, e to the 2x dx, that'll be v2 dv2, right? The differential of my second v, dv2, e to the 2x dx. Right? So differentiating u2, right? The second du, right? du2, the -3 sine of 3x, chain rule there. And then the second v, right? v2, be half e to the 2x again, right? Integrate. Right? And then going through the parts formula, just this integral, would be, u2 v2 uv, so u2 v2, this would be half e to the 2x cosine 3x minus the integral of v du, so v2 du2. Well, that'd be -3, so I multiply this and this, that'd be -3/2, so I pull out this +3/2 out here. And then e to the 2x sine of 3x dx. I forgot the dx again, sorry. There should be a dx on that differential. -3 sine 3x dx. Don't forget that. So e to the 2x sine 3x dx. Great. So I'm going to put this here into the orange box, and we're going to distribute the -3/2. Okay. So now I have this. Right, so going back up here, right, we have half e to the 2x sine of 3x, and then -3/2 times, and again, this orange box integral, in big parentheses, we're going to distribute the -3/2. That's this thing. Half e to the 2x cosine 3x. And we got +3/2 times the integral of e to the 2x sine of 3x. Yeah, I can use a parentheses here. So now I distribute this, both those terms, right? There's two terms here, two products. And we get the following. All right, so I'm gonna go back to, look at this integral here. All right, that should look familiar. I have the integral of e to the 2x times the sine of 3x dx. That's the integral we started with. So I should now be able to solve for this by taking all the terms with that integral on one side and then getting it alone, getting it to have a coefficient of 1. Well, after distributing the -3/2, we get this. So I have the integral of e to the 2x sine of 3x dx. This is times 1 right now. And the coefficient on this is 1. Equals all this. That equals 1/2 e to the 2x sine of 3x. And then after distributing this -3/2 here, we have -3/4 times e to the 2x cosine of 3x. And then -3/2 times +3/2 would be -9/4. -9/4 times this integral. The integral of e to the 2x sine of 3x dx. And again, look, I can get these on there. This product on the left has this integral, one of it. And on the right side of the equal sign, I have, -9/4 of the same thing. So I'm going to gather those to the left side. I'm going to add this 9/4 of this integral. And do it over here, right? It's an equation. So add 9/4 of this integral. Sorry, this is going to be crunched here. It's just adding the integral again, but 9/4 of it. And then these are just like terms. It's 1 of something plus 9/4 of that same thing. 1 plus 9/4, that's 4/4 plus 9/4. If I get a common denominator, that'd be 13/4 of that integral that we're looking for. And that's equal to, right, and I got rid of this over here, right? I added that. That's equal to all this stuff, right? All this stuff's left over that I just underlined. So it's equal to half e to the 2x sine of 3x minus 3/4 e to the 2x cosine 3x. And now finally, to get our integral by itself, right? I want to know what one of it is equal to, not 13/4 of it. So I'm going to multiply both sides by 4/13. Right, so all this times 4/13, right? We're distributing that, and we'll be done. And then, of course, when we're done, we add any constant, and we'll have the general antiderivative. So I'm getting here the integral that we want, right? The integral of e to the 2x times the sine of 3x is equal to, when I multiply 4/13 by a half, that'd be 2/13 times this e to the 2x sine of 3x, and then minus, and then 4/13 times 3/4. The 4's would cancel as 3/13, and then times e to the 2x cosine 3x. And there we go. That is this integral's primitive or basic antiderivative. And then you throw on any constant at all, and you'll get the general antiderivative, right? And that's what we want right there. Okay. Yeah, so we saw a couple examples of things like these now, right? Where you're performing parts, and after a while, right, after maybe a few steps performing parts, you see the same integral you started with. And then you can try solving for that, right? Gather all the terms with that integral to one side and then get it alone. Okay, so let me enter this. 2/13 times e to the 2x times the sine of 3x minus 3/13 times e to the 2x times the cosine of 3x, and then plus some constant. Right, don't forget that. Right. That's another parts more than once deal. So this time, I'm going to use the table method. It's been a few examples since I've done it. Because look at this product here. Polynomial, this time, right, instead of like, remember there was that example with e to the 3x to the 4th power? I can't integrate that. But I know how to integrate the sine of 2x. That's no problem. So because I have a polynomial times something I know how to integrate, I'm going to go to the table method and just, take the polynomial, differentiate it until I get a row with 0 in it, and we'll work with that. Right? So this will constitute, doing parts more than once. So I've got the integral 7x squared times the sine of 2x dx, right? Again, if there's a polynomial multiplied by something I know how to integrate, I'm just going to do this table method. Again, you can do the whole parts thing by the long way if you want. Remember, I got some differentiation column, integration column, alternating pluses and minuses for the rows. Again, I like to separate the rows. And I'll have, u be the polynomial, and the rest of it be the differential dv, right? So I'll have 7x squared, the polynomial in the differentiation column, and then just the sine of 2x in the integration column. And when I differentiate, right, this will be 14x, then 14, and I'll throw on one more row here until I get down to 0. Plus minus, and then down to 0. And then I'm integrating this. Now the integral of sine would be, negative cosine, Then I got the 2x in here, so I got to multiply by a half, and then do it again. It'd be negative, sine of 2x. If there was a half here times another half, that'd be a quarter. And then one more time, just to get to that row with the 0 in it, it'd be a integral of sine. It'd be positive 1/8 cosine to it. So my first UV would be this product here. So my first UV would be negative 7/2 x squared times the cosine of 2x. And then you'd be subtracting the integral of this product, right, this row, but that would produce this UV, right? So minus this UV, if you did parts again. So then minus this product, now that'd be minus 14 times negative 1/4, that's positive 14/4, positive 7/2, so plus 7/2, and then x times the sine of 2x, right? And then you would add the integral of this product, right, this row, which you know how to do. I could put that in plus the integral of negative 7/2 sine 2x. But if you did that parts again, you'd get plus this UV, right? And then this UV would be plus 14/8 or 7/4, right? Plus 7/4, and then just the cosine of 2x. And then finally, you'd have minus the integral of this product, this row. But this product is 0. The integral of 0 will be 0. So plus, minus 0. So there's no point in keeping on writing that. And then you can add on any constant to this, and there you go, right? This is our general antiderivative there. So yeah. So once again, if you have a product of two different kinds of functions, if one of them is a polynomial and the other one is something you know how to integrate multiple times over, I'd suggest this quick and easy table method here. All right. So we're entering, I had negative 7/2 times x squared times the cosine of 2x. All right. Then plus 7/2 times x times the sine of 2x. Then plus 7/4 times the cosine of 2x. And then, of course, at the end, plus some constant. Wonderful. So again, I have a polynomial, 3x squared times, now this is not e to the x squared, right? If it was e to the x squared, I couldn't do it. I can't integrate that. But it's e to the 2x. I know how to integrate e to the 2x, e to some linear power. So, just like the last example, was I have a polynomial multiplied by something I can integrate many times over in my head. I'm going to do that table method for, like this here in the last example to represent doing integration by parts multiple times. So we have the integral of 3x squared times e to the 2x dx. Once again, polynomial, I'm something I know how to integrate multiple times, right? Not just once, but you could integrate the integral and integrate that integral. And I can see how to do that with this, e to some linear power. Easy, easy, easy. So I got my differentiation column, I got my integration column, alternating pluses and minuses for each row. And I'm putting my u, right, in the stuff for dv. The thing I'm going to differentiate in the first column here, first row, first column, and the thing I'm going to integrate e to the 2x in the second column. If I keep differentiating, I'll eventually get down to 0, right? Yeah, 6x, and then 6, and then 0. And you can stop there because the rest of them will be 0. And then half, integrating here, half e to the 2x, quarter e to the 2x, and then an eighth e to the 2x, right? All right, so if I did parts the first time, this should be the UV, right? This product. So my first UV would be 3/2 e to the negative x squared 3 halves x squared e to the 2x. That'll be the first UV, this diagonal product. Then I'd be subtracting the integral of this product, which if I did parts again, the next UV would be this. All right, got these diagonal products here. So minus the product of 6x and, 1/4 e to the 2x. So 3 halves, 6/4, that'd be 3 halves x e to the 2x. 6x times that. And then we'd add the integral of this, which I could do. I could put plus the integral of 6 times a quarter e to the 2x dx. But if I did parts one more time, this would be the next UV, right? Maybe U3 times V3 if I call them that. So I'd have plus, this product, 6/8, which is 3/4 e to the 2x. And then we'd have minus the integral of this product. And the integral of this product would just be 0. So you could put minus 0, but then that's it. Right? There's our primitive antiderivative, and then I add on any constant I wish, and that's good. So those terms there. Great. So let's enter that. So 3 halves times x squared times e to the 2x power, then minus 3 halves times x times e to the 2x power, and then plus 3/4 times e to the 2x, and then of course after we're done, right, plus any constant plus c. All right, so we're done now with all of the indefinite integrals. So we'll move on now to definite integrals. So now we're going to be asked for the value of some definite integral, right? So we should end up with a number, right? We'll have limits of integration. So now we're doing use integration by parts for definite integrals. Nothing really changes here except you're going to have limits of integration, and right, the value is going to be a number. Right, so this is when your limits are numbers, constants, this is going to be equal to some constant, right? Remember, it represented like a net area under the graph of this curve to the x-axis or whatever, right? And notice they want us to enter answers using exact values, so don't enter it in a calculator. So that'll give you some decimal thing. They don't want decimal, so they want it exact. What would it be without rounding it? All right, so nothing changes except for the fact that there are now going to be limits of integration, right? So remember the parts formula. I've been putting up the parts formula a bunch of times throughout this video. That's the integral of u times dv equals u times v minus the integral of v times du. So now, all that changes is throwing limits on this. Say the integral from a to b of u dv is u times v evaluated at a and b, right? So remember, you put in b first, you put in a, and then subtract. And then this integral will also have limits. That's it. Okay, that's all that changes when it's a definite integral. So I'll put parts formula, definite integral. You have limits. So yeah, the example we're given here, we have the integral from 1 to 4. Right? So from x equals 1, this is dx, right? X equals 1 to x equals 4. And our integrand is 3x times the natural log of x cubed and dx. Yeah, so we've got a product here again. My integrand is a product of a polynomial and a log function. Now, again, from Calc 1, you don't know I mean, you might have memorized integrals of logs, but just log of x, probably not log of x cubed. Now you can pull the 3 out, using the power rule and whatnot if you want, but I'm not going to worry about that just yet. So yeah, I'm not going to use the table method, right? Because again, this natural log of x cubed, I mean, I could. I know if I pull the 3 out, I can integrate it pretty easily, but because it's not a readily available integral for me, it's not quick. I'm not going to use that table method. I'll just use but still, if I'm going through the Liate thing, I'm going to have u be the logarithm. That's LIA and a log first. So log is probably the best choice for u. And then the rest of it, the 3x dx, that'll be the dv. Okay, so I have u be the natural log of x cubed, and then dv, and I don't think I'm going to have to do this more than once, so I'll just keep calling them u and v instead of u1 and v1, be 3x, and then we differentiate the u to get du, because I want du over here on this right side, right? And this is just going to be 3 over x dx, right? Because this would be 1 over x cubed times 3x squared, or you could pull the 3 out, 3 times log x, 3 times 1 over x when I differentiate. And then here I'm integrating to get v, right? I want v on this side. And this would be 3 halves squared, right? Again, don't worry about the plus constant here. We'll throw the plus constant on at the very end. All right, so when I go through and fill in the parts formula here, that's u times v, so it'd be 3 halves. So it's 3 halves. No, wait, this is just a big bracket. 3 halves x squared times the natural log of x cubed. All right, there's uv. And then we're evaluating this from x equals 1 to x equals 4. And you know what? Now I might pull out the 3, use the power property for logarithms, just to make this so I don't have to raise things to the third power. I'll write that on the next page, though. All right, then minus, we're doing the integral from these same two limits, from x equals 1 to 4, of v du. And that's this product, v du. Now, 3 halves x squared times 3 over x would just be 9 halves x. I'll pull the 9 halves out, and I just have x, and then you still got the dx here too, right? So again, this would be 9 halves, and then x squared over x is x, 9 halves x. Pull the 9 halves out. All right. And I know how to integrate that, right? Integral of x is easy. So now on the next page, all right, so like I said, I'm gonna pull this power out. I remember the power property for logarithms. I can pull the 3 out here. Power property. So that'd be 9 halves times x squared, and then times just the natural log of x. All right, we're going from x equals 1 to x equals 4 here, and put in 4, put in 1, subtract. Then over here, when I take the derivative, antiderivative of x, that'd be half x squared, so I'd have 9 quarters, right? We're doing 9 quarters x squared, because I got the 9 halves out here times a half, 9 quarters x squared. And again, from x equals 1 to 4. And really, I can put these, since they're both from x equals 1 to 4, I can put them together. You know what? I'll do them separately. I'll do them separately. So this one here. Now, because there's a 9 halves constant factor, I'm going to pull that out. We have 9 halves pulled out, right? Times, when the value of this thing at 4, when I plug in 4 for x, that'd be 4 squared. That's 16 times the natural log of 4. 16 times the natural log of 4. Which I could also call, the 4 is 2 squared. I can make it 32 times the natural log of 2. Whatever. Minus, and then when I plug in 1, that'd be 1 times the natural log of 1 is 0. So there's this value, right? Then we're subtracting. Again, I can pull constant multiples out of this. So 9/4 times, and then the value of x squared at 4 and at 1 subtracted. So 16 minus 1. Right, that would be the value of x squared at 4 and at 1 subtracted. Okay. So 9, now the minus 0 is not necessary. So it is 9/2 times 16 log 4. So 2 goes into 16 8 times. 9 times 8, that's 72 times the natural log of 4. And then 9/4 times 15. All right, 16 minus 1, 15. 9 times 15 is 90, and 45, that's 135 fourths. Minus 135 fourths. And I'll enter this. Again, you can pull a power of 2 out of here, make it a 144 natural log of 2 minus 135 fourths. But this is it. And this is a number, right? This is a value. Now, if I want to check this out, if I want to test this out, let's go to Desmos. I go to some calculator here, and I can enter my integral. All right, the definite integral we were given, int. All right, let's type in int here. X equals 1, so x equals 4. And the integral we were given was 3x times the natural log x cubed, right, dx. And I'm getting this number, right, 66.063194, blah, 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 right? Now let me enter the answer I finally got, right? 72 times the natural log of 4, and then minus 135 fourths. And look at that. It's the same value to this many, an incredible number of decimal places. So our answer seems correct. I checked myself. Now, after this problem, I really won't be checking. Unless they ask me to round things, then I'll have to go to the calculator. Yeah, so we enter 72 times the natural log of 4, or 144 times the natural log of 2, minus 135 fourths. Great. Well, they had the natural log of 64 in there times 24. Right? So they put the third power back in. They kept it as x cubed, right? Remember I pulled the 3 out earlier? They kept it as x cubed, but it's still the same value. Okay, so I had this up earlier. We had our inverse trig. Let me see if I can find that sheet. Where did I throw that sheet? Yeah, we had our inverse trig derivatives, because that's going to be necessary here. I'm going to have u be this inverse trig function, inverse tangent of 2x. And we'll go from there. All right, so recall here I had this on a previous page, right? Ignore the right side. So when I have inverse tangent of something, right, the derivative 1 over 1 plus that thing squared. And again, there should be du here, but I didn't write the differentials, sorry. So keeping that, I'll keep that up. I'll keep that up so we can actually use it for a second. So our integral, we're given the integral from, this is again x, it's in terms of x dx. So x from x equals 0, x equals 1/2 of the inverse tangent of 2x, right? And then times your dx here. All right, so if I'm doing parts, right, I'm going to have just u be the inverse tangent. All right, so let's say u equals my inverse tangent of 2x there. And then you could do a u sub, but this is just a linear polynomial in here. So I don't feel the necessity for it. But if you want to do a u substitution and change, remember with definite integrals, you can also change the limits after you make a substitution. I'm not doing that here. Okay, you can if you want, but. And then dv will just be the rest of it, right? Just dx, 1 dx. All right, then du, differentiate this. Set over here for inverse tangent, it's 1 over 1 plus the expression inside the tangent, the argument squared, which 2x squared, 2x to the second would be 4x squared. And then times the derivative of the thing inside, right? So times 2. So times 2 up here, 1 times 2 is 2. And then you have, times the differential of x. And then when I integrate this, v is just x. V is just x. Okay. So parts formula. All right, so now I'm done with that derivative of the inverse tangent. I'll throw that sheet away. When I'm throwing it away, I might have to bring it back up later. So remember the integral of u dv is uv. So x times the inverse tangent of 2x. And we're evaluating this, right, from x equals 0 to x equals a half. Right, so I'll plug in a half, I plug in 0 and subtract. All right, minus the integral of v du, this product. So I can pull the 2 out if I want, but I'll leave it there. 2x over 1 plus 4x squared dx. And we're going from x equals 0, x equals a half. That's all that changes. I have these limits now. And now I want to evaluate this, right? So this value I can take right now. All right, you know what? I'm just going to, because I can do it right now. Let's just do it right now. So when I plug in a half, we'd have a half times the inverse tangent of 2 times a half, because it's 1. And this is something you should know from trigonometry. Remember, inverse tangent is some angle between negative pi over 2 and pi over 2 would have a tangent of positive 1. So this will be pi over 4 in a second. Minus, and then when I plug in 0, you just get 0 times whatever. And again, the inverse tangent of 0 would also be 0. That's just all 0. And this here, this inverse tangent of 1, is pi over 4 radians. All right, so I have this now. Half of pi over 4 would be pi over 8 minus 0. Right? So just pi over 8 is the value of this. And then we're subtracting, again, the integral from x equals 0 to a half of this thing, 2x dx in the numerator, and then 1 plus 4x squared in the denominator. Okay. So this one I could do a substitution for. Again, since I used u earlier, right, just to avoid confusion, I'll use t. So for this integral, I'm going to have t, right? We know the derivative of this quadratic down here would be a linear. I'm going to have t be that denominator, 1 plus 4x squared, placed it in whole denominator with t. Right, and then dt would be 8x dx. And if I want 8x dx, right, I've got 2x dx. I could just multiply by 4. Don't forget, if you multiply something by 4, you also have to multiply by 1/4, and I'll do that on the outside because it's going to be a constant multiple. So times 4 times 1/4, that's just like multiplying by 1, and that'll give me 8x dx up here, right? 8x dx, that's this. So that'll be dt, and then this will be t in the denominator. So, and then I change the limits as well, right? Remember, when you have definite integrals, you can also change the limits, right? So that way I don't have to go back to x. If I change, if I change the variables to be in the t domain, the t world, if you change the limits to be in t as well, you don't need to go back to the x. So let's change the limits as well. Right, so the original lower limit was x equals 0. Well, if x is 0 in my substitution here, t would be 1, right? 1 plus 0. And the new upper limit in the t world, in the t domain, the original was x equals half, right? The original upper limit was x equals a half. If I put a half in, a half squared is a quarter, 4 times a quarter is 1, 1 plus 1 is 2. We're just going from 1 to 2 in the t domain, in the t world. So yeah, so after making all these substitutions, we got, pi over 8, right? That was the value of the original, uv with put in a half, put in 0 and subtract. So I got pi over 8 minus, and then this quarter out here, right? Because I multiplied by 4 and a quarter, 4 and then by a quarter. So I got a quarter times the integral from t equals 1, right? The new lower limit is t equals 1 to t equals 2 of dt over t, or 1 over t dt. Same thing. And that's a really easy integral to take, right? 1 over x dx, 1 over y dy, 1 over w dw, right? This is the natural log of the absolute value of t. And because my values of t are already positive, we're going from 1 to 2, I don't need the absolute values on that. But this is a pi over 8 minus a quarter. And then this integral here is the natural log. And I'll keep the absolute value. Whatever, it's going to be positive stuff anyway. That's the natural log of t, from t equals 1 to t equals 2. Now, if I didn't change the limits, I'd have to go back to the x world. I'd have to go back and have t be 1 plus 4x squared, and then use 0 and a half. Okay, so if you don't change the limits, you got to go back to the original variable. All right, so we're almost done. Pi over 8 minus a quarter, right? And then times, and then this thing here would be the natural log of 2 minus the natural log of 1, but that's just 0. So we just a quarter the natural log of 2. So we finally get pi over 8 minus 1 quarter times the natural log of 2. There's the value of that initial definite integral. And again, you can go back to Desmos or some other calculator and check it out, right? Punch in the original definite integral and then punch in this number here, right, that we just found, and see that they're the same value to like 9, 10 decimal places, however many decimal places the calculator is showing. But I'm just going to enter this, right? So pi divided by 8 minus, and then a quarter natural log of 2. I'm just going to go natural log of 2 divided by 4. Call that. This should be good. Great. That's exactly how they entered it. All right. So now we got find area and volume problems. So this is going back to, now if you haven't watched my videos on sections from chapter 2 in these Newton Alta assignments, 2, 2, 2, 1, 2, 2, 2, 3, and 2, 4. Maybe go back to my channel and do a search in my channel for those, section 2, 2, 2, 3, 2, 4. 2, 1 was finding areas between curves. 2, 2 was finding volumes of solids of revolution, where I took a region on the plane and rotated it around some line to create a three-dimensional solid figure. And it was finding the volume of that using the disk method or the washer method. Section 2.3 was also finding the volumes of solids of revolution with the method of cylindrical shells. And then section 2.4 was on finding the length of an arc, right? The arc length of a curve over some interval. And the second half of section 2.4 was finding the surface area of a surface of revolution, right? Where you took a curve, just a curve, not a region, and rotated it around some line to create a surface, right? Some like sheet of paper wrapped up to create a surface. And we found the area of such a surface. So yeah, so we're seeing these problems again here, right? Use integration by parts to solve area problems and volume problems. So we're seeing those problems from chapter 2 here again, but this time, the integrals that get set up more than likely have to be done through this technique of integration to parts. Okay, so this is more complicated integrals to do things from chapter 2. All right. So here, finding the volume of a solid of revolution, right? A solid obtained by rotating the region bounded by this curve and the x-axis and the y-axis and the line x equals 1. So I'm going to draw that region, a rough sketch of that region, rotating around the y-axis and submit an exact answer. All right, so no rounding, no calculator. We can use a calculator to check our work at the end, of course, but let's go. So the region in question, the curve they gave us was f of x equals, it was 1/5 e to the 2x. So it was e to the 2x over 5. The other curves were the x-axis, the y-axis, and the vertical line x equals 1. So let's say here's x equals 1. If I were to plug 1 in here, that'd be e squared over 5, right? However high that is. Obviously, at the y-axis, that's when x is 0. And when x is 0, you get a fifth here, right? E to the 0 is 1. So you have a fifth. And that is an exponential that's increasing, right? E to a positive 2x. Something like that. There's our curve. There's f. And again, it's bounded by these curves, so it has to be touching all these curves. So here's x equals 1, right, vertical line here, the y-axis, the x-axis, right? So the region that is touching or bounded by all 4 of these curves is this shape here. Right, this region here, which I'll put in like a blue color, like that. Right? That's the region being discussed. And they're telling us, right, we're rotating this region, revolving it around the y-axis. So spinning it around here to create a three-dimensional figure, like almost like a bowl, right? Can you, if you can picture that, this would, if I took this region here and rotated around to create a three-dimensional shape, I'd create like a little bowl shape. And then what's the volume of that bowl? Now we can choose to do this integral setup using discs or washers. Thing about that though is, remember, for discs and washers, you're making slices perpendicular to the line you're rotating it around. So I'd have pretty much a cylinder up until y equals 1/5. And then after that, the curve changes, right? The left curve and right curve change. So I'd be doing two different volumes and then adding them up. Also, the radii, if I do that, I want things in terms of y. So how do we get, this is y equals 1/50 of the 2x. I mean, I could solve for x, it would have some natural log in it, but I don't like integrating things with natural log as much as I do with exponentials. So I'm going to do this by shells, right? Just through experience here. I can see we're going to do by method of cylindrical shell to find the volume of this bowl that's created. So I'm not going to go through the whole lesson again, right? Just go back to my section 2.3 video on, method of cylindrical shells. That's where you take a strip of the region here, some thin rectangular strip corresponding to some x value. You take a strip that's parallel to the line you're rotating around. So some vertical strip, they'll have some thickness of dx, and when I spin this around, right, if I were to take this strip and spin it around the y-axis, we'd get a shell, right? And a shell is just like a very thin it's just a rolled up piece of paper. The y-axis in the middle here. There's x equals 0, the y-axis going through the middle. Thickness of the shell is dx. The height of the shell is just this distance here, right? It's the distance from the x-axis, y equals 0, up to the curve. So it's just the y coordinate of this point on the curve, which if I have dx, I want things in terms of x. So the height here is the y coordinate on the curve, which in terms of x is 1/5 e to the 2x. So in terms of x, that's 1/5 e to the 2x, and then I would also like, the radius of the shell, right? How big is this circle? What's the radius of this circle? And that would be the x coordinate, right? It's from the line you rotated around to the curve. That's the radius of rotation. And that would be just the x coordinate, right? I'm moving right here. That's just the x coordinate of my point on the top of that rectangular strip there. And that's already in terms of x. So radius is x, height is 1/5 of the 2x, thickness dx. And remember, the volume of a shell it's just the circumference of rotation, so 2 pi r, times the height, and then times the thickness, right, times dx, and then we'll be integrating. And I've got r and h in terms of x already. So the volume, right, the volume of the solid, the bowl shape that would be created if I spun this around the y-axis, be the integral from, right, and I'd be taking rectangular strips like this and creating shells for every x value from 0 to 1. Right, so from x equals 0 to x equals 1 of these shell volumes. Now, because 2 pi is a constant, I'll put it out. I'll pull it out later. 2 pi times r, this is in terms of x, x times the height, right, 1/5 e to the 2x. That's your height in terms of x, and then times the thickness dx. All right, so I'm going to pull some constants out here. 2 pi over 5 can come out. So it's going to be 2 pi over 5 times the integral from x equals 0 to 1. And if I pull out 2 pi over 5, what I'm left with is x times e to the 2x dx. Right? So on the next page, I'm going to just focus on this integral here. We're going to do this by parts because I got a polynomial times an exponential, right? It's a product of two different kinds of functions, so parts might be a good idea. And then I'm going to multiply the result by 2 pi over 5. Yeah, so it's the same as in chapter 2, right? All those chapter 2 sections. It's just, the integral setup requires parts. So now I'm looking at the integral from x equals 0 to 1 of x times e to the 2x dx. All right, and once again, because this is a polynomial times something I know how to integrate, right? Integrating e to the 2x is no problem. I'm going to go to that table method. You don't have to. Differentiation column and integration column, alternating pluses and minuses here in each row. And, I'm going to have be x, and dv will be e to the 2x dx. So the thing I'm integrating is e to the 2x. If I differentiate this down the column here, that's 1, then 0. Integrating, I'd have half e to the 2x, and then a quarter e to the 2x. Right? And then the first time I do parts, this would be the uv, right? This product here, this diagonal. Okay, so this is going to be x times a half, right? So sorry, half x times e to the 2x, right? And we're going to be putting that for my first uv. And then we'd be subtracting the integral of this product, which if I did parts again, have this for the next uv. Right? So then minus, a quarter e to the 2x. I don't know why I put parentheses around this first one, but minus a quarter e to the 2x. And then we'd be adding the integral of this product in the next row, which is 0. So plus nothing. So here's our antiderivative. And then we're evaluating this from x equals 0, right, to x equals 1. So let's put in 1 first. So this would just be 1/2 e squared, right? Plug in 1/2 of 1 times e squared and then minus a quarter e squared. All right, so that's the value at 1, minus, and then the value at 0, well, this first term here would be nothing. So 0, and then minus a quarter, e to the 0 would be 1, so minus a quarter. All right, so this value here, half e squared minus a quarter e, that's 2/4 e squared minus 1/4 e squared, that's 1/4 e squared from this, and then minus negative 1/4 would be plus a quarter. All right, and then if I want to pull the quarter out, make this a quarter of e squared plus 1. All right, so that's the value of this integral. Now don't forget, this is going to be multiplied by 2 pi over 5. Remember, I pulled out 2 pi over 5 earlier. All right, so my total volume is, you know, I'm going to times that by 2 pi over 5. So that'd be 2 pi over 20, which would be pi over 10. Okay, pi over 10 times this e squared plus 1. And that would be cubic units, right? Don't forget it's a volume, right? So cubic units, which, oh, you know, they don't have the word cubic units there. I don't think you have to type it though. Just understand that it's a volume and it should be in cubic units. Yeah, so I'm just going to enter the number and see, hopefully they give it to me, right? Let's say cubic units or units cubed. So we have pi over 10 times the quantity, you know, e squared plus 1. Should be it. Wonderful. Yeah, so they actually just distributed the pi over 10, but it's the same value. All right, and again, they have the region, and down here you can see when I rotate that region around the y-axis, I create this bowl shape, right? You can move it around, see this thick, and they have a little cylindrical shell there in red, right? But we have just found the volume of that shape to be, you know, pi over 10 times the quantity e squared plus 1 cubic units. Okay, this one is just an area. All right, so no volume, just an area. All right, so the area bounded by the x-axis, the curve y equals inverse tangent of 3x, and x equals a third. So I'll draw that up, figure out what region they're talking about. So the curves we're given are y equals inverse tangent of 3x, right? So that hopefully you recall that, you know, that has a horizontal asymptote at pi over 2 and negative pi over 2, right? It never gets higher or lower than these. Inverse tangent, right? This is going back to trig. I'm not going to teach you trig again here. And then everything would be cut by a third, you know, a factor of a third, be compressed by a factor of a third. It's not just x, but it's 3x. So I still have 0, 0. But it would be 1/3, right? When I plug in 1/3, that'd be the inverse tangent of 1. That would give me pi over 4. And then same thing over here with negative 1/3 for the input would give me negative pi over 4. I don't know why I need to make the whole graph, but got these points. And then, you know, the curve looks like this. It's like, ooh, going through that. It's kind of like a cubic, but with these asymptotes, right? It's approaching this horizontal asymptote up here. Okay, it's something like this. Going from 0, 0 to this point here, pi over 3, 1/3, comma pi over 4, and then continuing on. But the other curves, right, were the x-axis and x equals 1/3, right? The x-axis was the other curve, and x equals 1/3 was the other curve that should be touching this region. All right, so the region is this region here. That's the region being talked about, this shaded region. So really it's just the integral of, you know, or if I take a little vertical strip here, little rectangle for some x value in between 0 and a third, thickness is dx. height of this thing is just the y coordinate to the top minus the y coordinate to the bottom. The y coordinate on the bottom is just 0, and the y coordinate on top is the inverse tangent of 3x. All right, so the area of this little rectangular strip is just that product, inverse tangent of 3x times dx, and we're adding those up for every x value. I'll be doing this for every x value from 0 to a third. All right, so the area of our region, integral from x equals 0 to 1/3 of the inverse tangent of 3x, right, dx. All right, and we saw an inverse tangent integral earlier in the video, but so I'm not going to bring that derivative feet back up. So yeah, so I'm going to do u sub here, let u be the inverse tangent. Not u sub, we're doing parts. So we're doing parts. Like always, like this whole video has been on parts. So I'm going to have u be that inverse tangent of 3x, and then dv be the rest of it, which would just be the differential dx. All right, now du. Remember, the inverse derivative of inverse tangent is something is 1 over 1 plus that thing squared, right? So 3x to the second would be 9x squared. But then chain rule, right? I got to multiply by the derivative of the thing inside, so times 3. And then you got, your dx. So there's your derivative there, and then v would just be x, right? You integrate this. So now I do the parts formula, right? Integral of u dv is uv x times the inverse tangent of 3x. All right, this will be evaluated from x equals 0, x equals a third, and then minus the integral of 3x over the integral of v du, right? V times du. So the integral of 3x over 1 plus 9x squared dx. And we're going from x equals 0 again to x equals a third. And then just like before, right, we saw an example very similar to this before. I'll evaluate this. Okay, so this real quick. When I plug in a third, there'd be a third times the inverse tangent of 1, right? But the inverse tangent of 1 is pi over 4. So a third of pi over 4, so this is pi over 12, right? 1/3 times pi over 4. And then minus 0, right? When x is 0, this is 0. So this whole value here is pi over 12. And now over here, I'm going to do this integral. And this one, I can see a nice substitution, right? If I let t replace the denominator here, right? Because remember, the derivative of this quadratic will be some linear. So t is 1 plus 9x squared. I'll have t represent that. And then the differential of t will be 18x times the differential of x. And if I want that to happen, here I've got 3x dx. If I want 18x dx, I can multiply by 6 and then also by 1 over 6 and pull, it's a constant multiple, so I can pull that outside. So this will be 1/6 outside the integral. And then we're going to change it to be in the t world instead of the x world, right? T domain. The new lower limit would be t equals, right? The original was x equals 0. When I plug that in, t would be 1. And the new upper limit, right? When x is a third squared is a ninth times 9 is 1, 1 plus 1 is 2, right? So we're going from t equals 1 to 2 now. And then this, right, is my 18x dx. So that's dt. And then this in the denominator, that's just t. So I get dt over t, right, or 1 over t dt. Very easy. Okay, so this is pi over 12 minus, and then just 1/6. And then this integral is no problem. It's the natural log of the absolute value of t, right, from 1 to 2. And we're getting the following, right? So it's pi over 12. When I plug in 2, this is natural log of 2. Plug in 1, you get 0. Natural log of 1 is 0. So this is just a natural log of 2 here altogether. So minus, the natural log of 2 divided by 6, right? All of that divided by 6. So there we go. and this would be an area, right? So that's square units, right? So the area of that region. There we go. All right, so I'm into that. Again, you can double check, go to calculator, enter the definite integral you set up, and enter the final answer and see that they're the same number. All right, so we got pi divided by 12 minus the natural log of 2 divided by 6. All right, great. And again, there's the region in question, right? You can kind of maybe zoom in on that, but that just that little shaded region there. That's all. So another definite integral with some parts here. Once again, I have an integrand where there's a polynomial x multiplied by something I know how to anti-differentiate, something I know the integral of multiple times over. I can do integrate, integrate again, integrate again. I can keep going. So I'm going to do that table thing here for this one. All right, so we got the integral from x equals 2 to 4 of x times e to the 4x. Yeah. So once again, because I have a polynomial times something I know how to integrate many, many times, I'm going to do a table. So I got differentiation column, integration column, alternating pluses and minuses for the rows. Should just need 3 here to get to 0. And then u is going to be the polynomial, and dv would involve e to the 4x dx. So I'm going to differentiate x, integrate e to the 4x. Now, if I differentiate x a bunch of times, you got 1, you got 0. I can stop at 0. And then integrating e to the 4x will give me a quarter e to the 4x. And then integrating again would be 1/16 e to the 4x. All right, and then if I was doing parts, the first uv would be this product. Okay, so this is 1/4 x e to the 4x. And then I would be subtracting the integral of this product in the second row. But if I did parts again, the next uv would be this product. All right, so then we have minus 1 times this, so minus 1/16 e to the 4x. And then I'd be adding the integral of this product in the third row. That's just 0, so plus nothing. And there we go. All right, so I'm going to pull out 1/16 e to the 4x from both of these terms. And if I do that, you'll have 4x minus 1 as the other factor, right? Because that'd be 1/4 x e to the 4x and then minus 1/16 e to the 4x, right? And we're evaluating this from x equals 2 to x equals 4, right? So plug in 4 first, plug in 2, and subtract. All right, when I plug in 4, this would be 16 minus 1, that's 15/16 times e to the 16th power. That's the value at 4. And then the value at 2, that's 8 minus 1, 7/16. And then 2 makes that e to the 8th power. Okay. And this is perfectly fine. You might even want to, you could pull out 1 e to the 8th over 16 here. They both have that as a common factor. And then you'd have 15 e to the 8th minus 7, the other factor. I mean, whatever. They're all the same value. And this should once again be, well, it didn't say it was an integral for an area or a volume or a length. Okay, so I don't know if this would be units or square units or cubic units, but because I don't know the context. Typically, it'll be like an area under a curve, but whatever. So I'm gonna enter that number. So we got, I'll put it in my factored form there. E to the 8th divided by 16 then that times the quantity 15 e to the 8 minus 7. So they wrote it out totally. They just distributed what I had. They had what I had earlier, right? All right, moving on. Getting there, we're getting there. Okay. So here's one with a polynomial times a logarithm. Again, logarithms aren't as nice as exponentials, right? If it was a logarithm, if it was a polynomial times an exponential or a polynomial times a sine or cosine with a linear function in it, right? Notice this is a cubic in here as well, a 3x cubed in the log. Uh, the times I use the table method are very specific. It's when there's a polynomial times something I know I can integrate a bunch of times without stopping. All right, so that's not really happening here. So I'll set it up and, do the Hartz formula. So we have the integral, dx again, everything in terms of x. So from x equals 1 to 4, and then our integrand is 3x cubed times the natural log of 3x cubed, and then dx, right? All right, so again, first section here, they're being pretty nice to you. If I stick with the Liate thing, it should work out. All right, so I'm going to have the natural log here. I'm going to have that be my u. And you can't pull the 3 out, right? Because 3 is not raised to the third power. You'd have to split this up to log 3 plus log x cubed if you want to pull the 3 out. But I'm not going to worry about that right now. All right. So I'm going to have u be this natural log of 3x cubed. And then dv, right, be the rest of it, right? The 3x cubed dx. I mean, you could also pull the 3 out in front here and just do x cubed dx, but remember to multiply by 3 at the end. Okay, then I want du. This will be 1 over 3x cubed times 9x squared. 1 over 3x cubed, then times the derivative of 3x cubed, right, 9x squared, and then dx. So that's 3 over x. This is 3 over x. 9 over 3 is 3, and then the who the x's would cancel. So 3 over x dx. And then for v, I'm integrating, right? This would be 3/4 x to the 4th, right? Okay, so our integral of u dv is uv. So this product, so 3/4 x to the 4th times the natural log of 3x squared, 3x cubed. All right, so that's going to be evaluated x equals 1 to 4. So we'll plug in 4, plug in 1, subtract. Then minus the integral from x equals 1 to 4 of v du, this product, which would be 9/4 x cubed. I'll pull the 9/4 outside, dx, because x fourth times 1 over x would be x cubed. And that's something I know how to integrate pretty easily. All right, so before we get to that, let me evaluate this. All right. And it's kind of gross, but if x were 4, 4 to the 4th divided by 4 would be 4 cubed. 4 cubed is 64. Then we got times 3. All right, 3 times 64 would be 192. All right, 3 times 64, 180 plus 12. It says 192 times the natural log of 192, right? 3 times 64. So that's when x is 4. When x is 1, the natural log of 3 is there. So this is 3 minus 3/4 times the natural log of 3. So there's the value of that first integral, right? The first UV. Let's double check in here, making sure I didn't make any errors. Okay. All right, then this one here, we got minus. Now when I do the integral of x to the third, I do 1/4 x to the fourth. I'll pull the fourth out, so 9/16. And then we're just looking at x to the fourth, right, between x equals 1 and 4. So this would be minus 9/16 times, 4 to the fourth. And I'll put the negative 9/16 back in. 4 to the fourth minus 1 to the fourth. And if I distribute the negative 9/16 here, minus, 16 is 4 squared. 4 to the fourth over 4 squared will just be 4 squared. So I have 16. 9 times 16 is 144. And then plus 9/16. You're right. We can get a common denominator if we want, but I've got this plus this. Okay, so all this together, I'm just going to type all this out. Forget putting them together. I don't really care. All right, because if I enter a number that's equivalent to what they want, they'll give it to me. I have 192 times the natural log of 192 minus 3/4 times the natural log of 3 minus 144 plus 9/16. Let's do that. 192 is the natural log. 192 minus 3 times the natural log of 3 divided by 4, right? 3/4 of the natural log of 3. Then I had minus 144 plus 9/16. Probably should put that together, but yeah. So again, as long as it's equal. So see, they put those two. Yeah. So they have basically the same thing. They just put these two together, make negative 2,295 over 16, get a common denominator, all that. Ugh. Okay. All right. So last time, this is it. Last objective. I got probably a couple more problems to go here. 2 or 3, maybe 4. These area and volume problems. So set up an integral. Submit an exact answer. So here we're given a region. Find the volume of the solid, and they even tell us to use shells this time. So that's nice. To worry about like what method we're using or think about it too much. Find the volume of the solid obtained by rotating the region bounded by this curve, y equals 5 times the cosine of pi x, the x-axis, the y-axis, and the line x equals 1/2. And we're rotating it or revolving it around the y-axis. So I'm going to draw that region to the best of my abilities. So they gave us y equals, or f of x equals, 5 times the cosine of pi x. They said the x-axis should touch it as well, the y-axis should touch it as well, and also the line x equals 1/2. Now x equals 1/2, kind of a giveaway here. That's a vertical line. We got the x-axis, the y-axis, right? So this is going to start at x equals 0 then. The y-axis is at x equals 0. And when x equals 0, right, the cosine of 0 was 1. So you'd go up to 0, 5, right? The output would be 5 for this curve. And then when x equals 1/2, pi over 2, cosine of pi over 2 is 0. And this is going to be some kind of a wave. Remember, a cosine wave? Yeah, something like that. I'll say it's something like that. Okay? Rough sketch. Probably not perfect, but it's good enough. And, the x-axis, y-axis, x equals 1/2. We're talking this region. And this region, right, is being rotated around the y-axis. So I'd create some kind of a dome shape, right? I'd create like a dome, a solid dome that's filled with material. And we're trying to find the volume of this. Now, they told us to do cylindrical shells. If I'm doing shells, right, remember I'm making a slice here, taking a thin strip of my region that's parallel to the line that we're rotating around. So that's going to be some vertical rectangle here corresponding to some value of x. It'll have a thickness of dx, right, some little change in x. I want the height of it. All right, I did shells in an earlier problem, and again, you can go back to my section 2-3 video on this. The height of this thing in terms of x is just the y coordinate of the top minus the y coordinate on the bottom. Well, that's just, the curve here, y coordinate on the top point is 5 cosine pi x. And the y coordinate on the bottom is 0, so you go minus 0, but don't need to write minus 0. And then when I rotate this strip around, right, we create a radius of rotation here. Right, that's from the line you're rotating around to the curve, right? Radius of rotation, and that's just the x coordinate of the rectangle I'm at. Radius is just x, and that's already in terms of x. Right? I don't need to get it in terms of y or anything. All right, so the total volume of this dome shape that would create this solid dome. All right, I'd be doing this. I'd be making shells like this for every x value from 0 to a half. So I'd be integrating from x equals 0 to a half. Remember the volume of a shell was the circumference of rotation, right? 2 pi r. R in terms of x here is x, the radius of rotation of the circle of rotation, times the height. And we said the height of the shell for any x is going to be 5 times the cosine of pi x. And then times the thickness, right, which is just a little dx there. Now if I simplify this a tad, 2 pi and 5 are constant multiples. Those can come outside. So that's 10 pi being pulled out here. And we'll have the integral x equals 0 to 1 half of x times the cosine of pi x dx. Now, this is a linear in here, pi times x to the first. So you could make a u substitution if you want and change the limits and get this in terms of u or t or whatever variable you want. But because it's a linear in there, I'm going to keep it this way. And it's another one of those where I have a polynomial, x, times, just a basic cosine of a linear. And I know how to integrate cosines and sines of linears all day long. Keep integrating, step by step. So because of that, I'm going to do this with the table method. So again, this integral, I'm going to focus on, and then whatever value I find here, just remember, we got to multiply by 10 pi at the end. So I'm going to have my differentiation column, my integration column, alternating pluses and minuses in each row. I should only need 3 of them. I'll have u be x, right? That's the thing I'm going to differentiate. So then 1, then 0. And the thing I'm going to integrate is the rest of it, right? Cosine of pi x. I'd have dv was cosine pi x dx. Integrating this should be sine of pi x, but then times 1 over pi, right? To counteract that pi times x there, right? And then if I integrate this again, there'd be negative cosine of pi x, and then times 1 over pi again, so you'd have 1 over pi squared. All right, so if I'm doing parts, right, the first uv would be this product, right, this diagonal, uv. Okay, so this integral here, and the thing in the box, is going to be uv, so 1 over pi times x times the sine of pi x, right, first uv. Then we'd be subtracting the integral of the product of the next row, which I could do easy. I could write that minus that integral. But if I were to do parts again, right, the next uv would be this diagonal product here. So then minus, negative, so it's a minus and negative product, so it's plus 1 over pi squared times the cosine of pi, right? And then we would be adding the integral of this product in the third row, which is 0, so plus nothing. All right, so I've got this as my antiderivative, and we're going from x equals 0, right, x equals a half. So I'm plugging in a half first, plugging in 0, subtracting, and then don't forget, I got the 10 pi times all this at the end, right? I pulled the 10 pi out earlier. So this is 10 pi times, when I plug in a half, sine of pi over 2, that was 1. So I got 1 times a half times 1 over pi. So that'd be 1 over 2 pi, right? 1 over 2 pi. And I plug in a half here. Now, cosine of pi over 2 is 0, so plus nothing. So the value at 1 half is just 1 over 2 pi. And the value at 0, well, the sine of 0 times 0, that's all 0, plus, and then cosine of 0 was 1. So you got, 1 over pi squared there. All right, so really, I don't need the parentheses around these. It's 1 over 2 pi at a half and 1 over pi squared at 0. And now I'm going to multiply this by 10 pi, right? Put 10 pi in. All right, so 10 pi over 2 pi, that'd just be 5. And then minus, 10 pi over pi squared would be minus 10 over pi, right? Because, the pi's would cancel. And there we have it, right? And that would be a volume, right? That's the volume of the three-dimensional dome solid that I would create by rotating that region around the y-axis. So this is going to be, cubic units. It's a volume. But just 5 minus 10 over pi. Right? So volume 5 minus 10 over pi. Right. They have they wrote the terms in the other order, but it's still the same thing. All right, and there's the region being talked about, right? You can zoom in. This is the region I drew, rotated around the y-axis, and create this, this dome, this tall mound. Right, we're finding the volume of this mound, which is, 5 minus 10 over pi, cubic units. Great. All right. All right, so this one's not a volume. It's an area problem. So again, I'm going to draw a picture of the region that they want us to find the area of and set up an integral and evaluate it, right? They want another exact answer. So the curves were given. It says the area, calculate the area bounded by the x-axis. Y equals negative x times e to the 2x between x equals negative 1 and x equals 0. So that's just the integral of this over this interval, right? If I drew this, I'll draw this picture. I'll draw it. Um, So between x equals, they said x equals negative 1 and x equals 0. Right? And also the x-axis. X-axis, I'll make that thick. And the curve is y equals, negative x times e to the 2x. Now at negative 1, be positive 1 e to the negative 2. That's some e to the negative 2, that's 1 over e squared. So it's 1 over e squared, 1 over e squared. Some positive number here at negative 1. And then at 0, you got 0. All right, and it's for all these negative values, this will be positive. So I don't really know exactly how the curve looks. Maybe if I wanted to do some more calculus stuff and plug in more points or whatever, I could figure out if it was concave down or concave up. But there's our curve. It's something like this. If you want to go to Desmos and get a better picture, but this is it right here. And x equals negative 1 is this line here. X equals 0 is the y-axis, and the x-axis is here. The only region that's being touched by all three of these is this region here. So, and if I were to make a little strip, a little rectangle in here, all right, little strip, little thin rectangle for some x coordinate, it has a thickness of dx. The area of this little rectangle, right, would be the height of it which is the y coordinate to the top minus the y coordinate at the bottom. Now the y coordinate at the top is what we're is that on this curve is negative x e to the 2x minus 0, right? The y coordinate on the bottom. So that's it. So we're integrating this times dx, right? We're going to have this times dx for the area of this thin strip, and we're doing this for every x value from -1 to 0, right? So the total area of the region in question, the integral from -1 to 0 of negative x times e to the 2x, dx. Right, and then like before, right, we've seen several examples like this now where I have a polynomial, negative x, times something I know how to integrate all day long. I know how to integrate the integral and integrate that integral, right, e to the 2x, very easy. So I'm going to make my little table, differentiation column, integration column, alternate pluses and minuses. And again, because this is the first power here, I should only need 3. Usually whatever power the polynomial is, you only need 2 more rows than that. Each row here. Stuff I would say u is negative x, and we'll differentiate that. So -1, then 0, down to zeros. And then e to the 2x is the thing I'd be integrating, right? I'd have dv be e to the 2x dx, right? So this would be u, this would be dv. And I'd be integrating this, right? So half e to the 2x, and then a quarter e to the 2x, right, when I integrate again. So if I'm doing parts, right, the first uv is this, diagonal product here. So this would be a negative half x e to the 2x. And then we would be subtracting the integral of this product in the second row. But if I did parts again, right, the next uv would be this product, this diagonal. So we have minus, and then, negative a quarter, so plus a quarter times just e to the 2x. And then we'd be adding the integral of the product in this third row, but that's just 0, so plus 0. So that's it. And we're evaluating this from x equals -1 to x equals 0. Now you could factor this, whatever. I'm just going to do it. All right. So first I'll plug in 0. Now when I plug in 0, right, this is 0. And then we have a quarter e to the 0. That's just a quarter. So that's the value at 0. Quarter. When I plug in -1, this will be more minus, and then the value at -1, that'll be 1/2, positive 1/2, e to the -2nd. And then plus a quarter, e to the -2nd. And putting these together, that's 1/2, that's 2 quarters, plus 1 quarter, that's 3 quarters. Right, this is 3 quarters, e to the -2nd. We're subtracting that. So I have all told here. Sorry, I'm going to bring this up here. So this is 1 quarter minus 3 quarters times e to the -2nd. Or you could put the e squared in the denominator, make this 3 over 4 e squared. But there you go, and that would be square units, right? Square units, because it's an area of a region. So we got 1 quarter minus 3 quarters times e to the -2 power. Or just 3 over 4 e squared. They probably have it that way. Yeah, they put the e squared in the denominator there, but it's the same value. Ah, thank goodness. All right. So after 4 hours plus, done with the assignment. Great. Yeah, but you saw it, right? The integral of udv equals uv minus the integral of v du. And how easy it is depends on your choice of u and dv, right? And you can use that LIATE, LIATE acronym to help you out, logarithms. If there's a logarithm as a factor or something with logarithms as a factor of your integrand, maybe that would be a good choice of u. If not, if there's an inverse, right, the I is inverse trigs, right, inverse tangent, sine, cosine, maybe make that u. If not, is there a polynomial, some arithmetic function, a polynomial or a radical with like square roots, cube roots, right? Basically power functions, things to powers, x to powers, rational powers, rational powers. You could probably do irrational powers too, but haven't seen too many of those. Try that for you if the L and the I aren't there, right? And then after A is T, you got trig functions, right? Try that. After T is exponentials if nothing else is there. And again, the Liate thing doesn't always work. It worked every time here because, they are introducing integration by parts to us. All right, so they're being kind, where the Liate acronym, that mnemonic device, works every time. I'm warning you, doesn't always work like that. Those aren't always the best choice of you. And then, of course, you saw that when you integrate things multiple times by parts, you might come across, an integral that's exactly the same as the integral you started with. So then you can solve for that, right? Gather all the terms with that integral to one side and then, get it alone. Divide by some number, get it by itself. Lots of stuff here. Lots of stuff here, right? Obviously, 4 hours plus here. Um, so, as I said at the very top of the video, the questions I saw here, right, are not going to be exactly the same as the ones you see when you work on the assignment yourself. But I'm hoping they're similar enough that, watching me do them here will help you out when you're working on them on your own. And thank you very much for watching.